Hey, everybody. Welcome. Thanks for coming. Good morning. Yes. I'm gonna share my screen. Okay. I think we're just gonna give people a few minutes to trickle in here. And then I'll do the intro again for the people that missed it yesterday. See the audiences filling up. Hey, Gail. Nice to see you. Welcome. Mm, okay, I guess I'll start giving the. Oh yeah, did you guys notice I turned on reactions this time, so now we can all show our pleasure or displeasure accordingly. Should make this fun. All right. Yeah, you guys get it. That's the spirit. I'm gonna go ahead and get this started. Um, Hello again, everybody. Welcome to day two of the Space Ecology Workshop. Um, Thanks for making it here early in the morning or late at night, as it were, especially after we had that full day yesterday. Which, man, what a workshop! There were so many excellent talks. Really feeling enthusiastic and jazzed up for today after that. So thanks again to all of our speakers from yesterday, especially those that were coming in at the last minute to fill in some spots. And also thanks, of course, to all the people who were impacted by the hurricane, but still managed to make it out. Um, so I guess without further ado, this is the day two of the third annual International Space Ecology Workshop. Um, I'm giving this same talk just in case people missed it yesterday. The reason we put this on a Friday and Saturday is so that hopefully people can make at least one of the days, if not both. So I'm expecting that the audience is a slightly different composition. Um, so if you missed it, the goal of this workshop is to try to advance the state of the art of supporting life in space. And of course, here on Earth, life always occurs in an ecosystem context. So part of the purpose of this workshop is to encourage people to broaden their science pursuits in space to include that greater multi-trophic context, so we can get closer to our goal of supporting sustainable living on Earth as well as in space, so we can achieve our best future, perhaps. The call to action for this workshop is to make an effort to doing cross-disciplinary collaborations with our colleagues. I thought yesterday was a really great example of that when we got to hear from not just people working on space agriculture, but also the industry, like the commercial companies that are working in the space, also artists working in this space. That's a really important part. It takes a village to create a community in on Earth, but also in orbit, and so we want to bring everyone with us. Whoops, other computer. Yeah, in case you guys missed it, after the very first Space Ecology Workshop a few years ago, it was quite an interactive workshop. We did a lot of like collaborative brainstorming where we were trying to identify technology and knowledge gaps so that we could build a roadmap to the perhaps Biosphere 3 in space. Um, that's all in this paper that was published at the International Conference on Environmental Systems. If you would like to know where you can contribute, I would recommend that you check out this paper because it has even prioritized lists of the sorts of obstacles between us and realizing this dream. Um, Again, quickly, the people that helped put this together, there's myself, Jane, Marshall. You're going to be hearing from both of them today. Jane is going to be giving one of the featured talks, How to Build a Biosphere, which I think everyone's going to be excited for. And Marshall's giving a presentation as well. Yesterday, Frida was giving a talk, which was a really nice connection to the very early days of pioneering closed ecological systems and their impacts on life support. And then, of course, we've also got Steven, who helps us hold it down in the back end. So day one agenda is kind of irrelevant. Day two agenda is slightly different from yesterday in that our featured speakers are bookending the whole day. Up first, we've got Volker, who is very graciously joining us from Australia at an ungodly hour to give the first talk. And then Jane is going to be finishing it up at the end of the day. In between, we'll have a bunch of shorter presentations and we'll have some coffee breaks interspersed so it doesn't get too dry. It is BYOC, bring your own coffee. Yeah, I guess, yeah. If you're an attendee, your mic and your camera are off. This time I found the setting so that when panelists join, their microphones are also off by default. So that should help. Yeah, but if you want to communicate, please do, especially in the chat box. And if you have a specific question for a speaker, you should put it in the Q&A box. Note that if you are a panelist, aka speaker, you can't actually use the Q&A, and in that case, you can just message the question to me directly or throw it in the general chat anyway, and people will find it. Yeah, like I said, we're not doing any collaborative whiteboarding or breakout rooms, networking things. They didn't get too much traction last year. We're open to changing that if people want it, though. And of course, we are going to record. This is already being recorded, and so next week probably I'll upload the recordings of the day one and the day two, as well as the transcript of the chat log, which is nice in case you want to look up links or studies that people had posted there. So I think that is it. Yeah. In that case, there's no need to delay any longer. I think, Volker, you want to get us started?
Yes, I can get started. So let me just do it. Okay. Do you see my slides?
Yep.
Okay. So let me just a second. Okay, then I start. Yeah. Good morning to you all. I'm really happy to present here. And thank you, Patrick, for this. And also thanks to Christine Escobar, who changed the time slot with me to make it possible. I presented a time which is good for my biorism. I talk today about modeling of spacecraft dishes for astronauts and also what we do with digital twins. I'm affiliated with the School of Chemical Engineering at the University of Adelaide in Australia, and we have the ARC Center of Excellence plans for space, which I will show in a second. And we have also the Andy Thomas Center for Space Resources. Andy Thomas is somebody from Adelaide who was the first astronaut from Australia in 1973 going to space. And I'm also affiliated with the University of Warwick in the UK. Now, what you see below is I come from frontier technologies, and one of those technologies is microfluidics or flow chemistry. 94, nobody did know about flow chemistry. Today it's a billion market, yeah. So that has really evolved to industry, and COVID jabs from Pfizer are produced with flow chemistry. So I was always interested in radical changes, in step changes. And when space research was evolving in Australia, around about 5, 6 years ago, when the space agency was founded here in Adelaide, then I thought, yes, this is something for me, and I want to do that. In the picture 2024, you see me at the Space Center in Leicester in England. And right to this, you see the first Australian space experiment with NASA and ISS, which I have headed 3 years ago. Now the contents of my talk. I will show you, we made a review, digital twins in agriculture. I will give you the extract out of that. I will talk briefly about the ARC Center plans for space. And then we will come to the modeling study of optimal nutrient dish for astronauts. And I will present majorly 2 digital twin studies, both with lettuce growth. One is on extreme weather, which is a space analogon, and the other one is done in 6 different climate zones. So this relates to the expected extreme climate in 2050, and how can we make plants ready to survive under those conditions. Finally, but only on one slide, I will show a future development where we make digital twins for aroma. I think we all agree it's very important not to get only nutrition in space, but to enjoy it, to have well-being in space. So flavor and aroma is an essential part of that. And I come from an engineering department. I just want to make clear here on the first slide that for the physical twins, which are experiments, we have a lot of innovations, which I will not show all in this presentation, but I like to summarize it here. We have precision engineered nanofertilizers. We leach regulate to get fertilizers. We have an entirely new UV sterilization method. We use aerosol microsprays. We can monitor the flow in a shoot in the plant with sensors. We use hydrogels, and we have simulated cosmic radiation as many people, we have also simulated microgravity. And just to show you what a precision engineered nanofertilizer means, here you see those necklaces, and these are cores of fertilizers, phosphorus fertilizers in this case, and we can wave that to a mesh, what you see below, and the mesh can be stacked. Then you have a 3-dimensional control on the micrometer scale of the nutrient release. And since this is a controlled release fertilizer, you have also the temporal domain. So finally, I would call this a 4-dimensional fertilizer. And on top of that, we put it in a new kind of hydrogel. So that is things which we are doing. But let me focus now on the topic of the talk, which is digital twins. They have become quite important in precision farming, and I would say we have not seen 10% of this. So there's a lot of room for evolvement. Digital twins are quite common in aerospace, in automotive manufacturing, in agriculture. They just have started to enter. We made a review on this, and since we are very interested in sustainability, we made the review along the life cycle. Now, digital twins are part of the Agriculture for Zero framework. There's a lot of optimism about the use of it. And last but not least, they allow rapid decision making. That is what I want to show. So the right term for this is multi-agent system. So the new digital twins are like a number of experts who talk together and make a decision. That is called multi-agent system. Now let me come to Plants for Space. We were very lucky to have this project from the Australian Research Council, ARC, and this is a center of excellence. This has really magnitude and impact. Yeah, the center runs 7 years, but likely it will run 10 years. So it runs a whole decade. The center has 35 million cash and some in-kind, which you see here, but we already made around about 10 or 15 million extra cash. So once you have the center, this is like a cash machine, and we expect to get $100 million finally in cash. It's a virtual center, so there's no building, no room for this, and it's an international collaboration, and I've seen that Gioia Massa from NASA is present in this talk. So we have NASA as a partner, as you will see on the following slide. We want to enable or give our small contribution to the human deep space exploration to on Earth sustainability. And we do that through plant and food design. Now here you see the topics which the center covers. I told you it's 10 years, so you can be a bit ambitious, and you see a lot of topics around plant and food, but also on system engineering, which I do, on psychology, which is important if you want to enjoy plants. And these are the partners. So this is Melbourne, Perth, and Adelaide as node partners. And then we have top universities as partners, and among them, as to be expected, a number of US university, which you see here, like the University of Davis in Arizona and more. You see also the University of Cambridge. Then we have space companies like Axiom Space, NASA, DLR, which is a German space agency, and more. We have companies who develop space systems. The company Gaia is in Melbourne at La Trobe University, and that is the only non-US company who is in the space contest of NASA among, I think, the last 10 companies who fight for the best horticulture product. So we are quite proud that an Australian company is in this last selection. And we have some platform companies. We have the Australian government, the government of South Australia, and the Australian Space Agency. This is a bit the vision. To this audience, I don't have to explain that at all. We go for vertical farming. We do farming in soil, but also naturally we focus on hydroponic and aeroponic systems. So we want to develop new kinds of plants for new kinds of food with new kinds of flavor. Recycling is a must in space. Again, this is not further to be explained in this audience. It's a center of excellence. So this is not a singular approach, but the approach of teams. And space law is guiding our development. And finally, we go for materials like bioplastics, but also most importantly for biomedicines, meaning we want to reprogram plants not to give only food and proteins and carbohydrates and so on, but also to act as chemical biomanufacturers. Now we have 4 missions: zero waste plants. We have the mission of complete nutrition, and that is what I talked today about. On-demand bioresource production, which I will not talk about, and we want to give our contribution to the future workforce in space, at least in Australia. Now, this is the first study I want to talk about, 1 out of 3. And this is about giving complete nutrient modeling for astronaut food. To be exact, it's for a male astronaut, and we refer to a paper where also NASA was co-author, where they defined how a nutrition for a male astronaut should look like. And then we do it in 3 steps, as you see by the picture with the icon and also by this graphical abstract picture. The first step is done by modeling. We want to ensure that the astronaut gets the right caloric profile, and most importantly, that's why it's in the middle, he gets all of the nutrients as defined in the paper. And then we do not want that the astronaut has to eat too much for it, so he might get increase in weight. So we give a maximal weight of around about 2 kilograms for eating. That's what we need because we consider vegetarian food. I have to mention this here. So we considered meat only in the second place. So our study is on vegetarian food. Then we have those nice to have constraints, compliance with Space Agency, foremost NASA. We would like to look on plants which have been proven to grow very well in space and so on. And then in the third step, we look on circularity constraints. We look on productivity and on palatability. That's where the psychology comes into place. Now, we made a paper on biofortification for space farming. We looked on lettuce. Lettuce is, at this point, our favorite plants, and we made 5, 6, 7 papers on it. And you see, we looked in 2 scenarios, 1 and 2, and we looked on different lettuce varieties, and I think you all know them, the butterhead, red leaf, and green leaf, and so on, and different mixtures of them. And then we defined this kind of traffic light analysis, so red for impossible, green for possible, and yellow for in between. And so we looked how those lettuces could give a complete nutrition for an astronaut. And naturally, nobody would eat only lettuce. I come on the next slide to a more realistic scenario for a space dish. I'd like to mention that in addition in this review, we talked about biofortification. So we compiled all literature approaches on intensifying the nutrient contents in lettuce. And that's exactly what we want to do in Plant for Space. We want to do this all at one time. Now I come to the realistic approach. We looked on finally 102 crops, which you see on the left side of this table. And we looked on the macronutrients and micronutrients, which were listed for those crops. And okay, I'm not a food engineer, finally, I'm a chemical engineer. To my really surprise, that was a difficult issue. There's quite some documentation on micro and macronutrients in literature, but it's far from being complete, and we want it to be complete. So you always read, when you look under vitamins, that some are excluded because there was basically no information available. At least we didn't find it. I think that's an interesting point to consider when you want to model really the perfect food in future. So finally, we had 102 crops, and we could make the modeling, and we looked at the maximum food intake. I said before 2 kilograms, but that was wrong. Here it's given it's 1.2 kilograms per day. And some of those scenarios which we defined fulfilled that, while other didn't fulfill it. We looked at 10 scenarios. 4 or 5 of them are full vegetarian food, as the other one add meat, fish, or chicken to the vegetarian food. Now here you see listed what we looked in detail. And the best scenario that I can say already now is the scenario 4. And if you look there, what kind of crops are in, it is, sorry, soybean, poppy, barley. It is kale, peanuts, sweet potato, and sunflower. And you see the weight contribution. So you already get now the information that sweet potato makes up more than half of this, what we called a space salad. You also see the animal food, which is not given for the scenario 1, 3, and 4. 2 is excluded here, but we have animal parts in the scenarios 5 to 10. Now, if you just compare scenario 1 and 3, you see, look down on it, total food weight. Scenario 1 has around about 2.2 kilograms, and scenario 3 has 1.1 kilogram. And the delivery of nutrients is essentially the same. So we would prefer 3/1. But finally, we found that scenario 4 is the best scenario. And we have called that space salad, as I will show you in a second. Now here you see the contributions. I admit that this black and white color coding is not easy to look on. 53% of the full vegetarian scenario 4 is the sweet potato, and then the next largest part is 19%, which is barley. What you can learn from the scenario 5, which is with meat, is that if you bring in meat, which has a lot of, especially micronutrient, foremost vitamin D, that you can have a bit more diverse mixture of the vegetables. Now, we were interested in sustainability, and we made several plots in the paper, and I don't need to show them all. I just show one of them. This is the planting area. A spacecraft is compact, that is clear. So we need plants which grow very fast, respectively need a low planting area. What you see then is that poppy takes the highest share, at least in scenario 1, for the planting area, and barley takes the highest share in scenario 3 and also in 4. Now, if we look back, here you see that barley and poppy form only a minor part of the space salad, while the sweet potato forms the major part. So there's no correlation. Actually, there's an anti-correlation between the value for nutrition and the plant area, meaning that when we consider the second step out of the 3, which I mentioned, we probably would have to revise our modeling. But as said, the modeling was only done for the first step. So what do we learn here? And that is not a surprise. Everything is a bit complex. When we look at fertilizer usage, we also see a pattern, and we see it's best for the scenario 5, 6, and 7, which have meat, basically because we need less vegetables here. Now, we made a psychology test, and I have to give my highest credits to Carolina Rivera Osorio from the University of New York. And we did the study under the umbrella of this university. But Carolina was also part of NASA's Venus New Exploration Area in space psychology. And they made a quick space test, which is not a quick space psychology test, which is not a proper psychology test, I admit, but it was something still we like to add here. You see, we had 4 volunteers. They were positive about the salad. They were also critical. So we learned a bit about the space dishes, and this is something we like to do much more in Plants for Space. Now, the American Chemical Society highlighted our paper under the title Designing the Perfect Meal to Feed Long-Term Space Travelers. And while I know, and I'm quite active with social media, while I know that space topics are very welcome among journalists, this press issue was really uh, never seen before. We had round about 100 press releases after this in all languages. You see one from Sao Paulo in Brazil in Portuguese below. So I show some of them here. So space food is really seemingly very interesting for the general public. Now, in a bigger picture, I mentioned we had 5, 6 papers on lettuce. We proposed a circular bioprocess for growing lettuce in the lunar space with phosphorus nutrient recovery in this paper. We made a paper where we looked on 50 years space farming, horticulture, and it starts in 1973. I've copied in here from 1982 and 1992, some Russian experiments and some NASA experiments. So we summarized them all, and this table is 3 pages long. Yeah, that's why I gave only a few years here. And we have made also a paper on U stress in space. We all know there's stress in space, and stress is sometimes good, like the stress now on me to talk at 2 o'clock in the morning in Australia. Stress is not always negative, and plants can maybe develop better under stress. Now I come to the digital twin studies. I will give 2 and a small additional third one. So our strength is not computer modeling. We are not computer engineers. Our strength is physical twins to make experiments. We are chemical engineers. And our first contribution to literature is that we said you should have 2 physical twins. One is a physical twin sender, one is a receiver. Why is that? In space, I made the first Australian space experiment. In space, the big limitation is you cannot replicate the experiment. You cannot reproduce it, at least not if you have not a lot of money. So I would have loved to replicate my space experiment, but it was not possible. So given that the space experiment can be only done one time, you can send the data from the space experiment to ground and repeat it on a microgravity machine, for example, and then you have all the statistics which finally give good experiments. So that is the idea behind this concept. And then you do what you always do in digital twins. You use machine learning for getting a model. The study was done in Spain, and the people who are kindly helped are mentioned here. Now, we wanted extreme conditions. Where do you get them? When you have to work near Barcelona in Spain, there's a mountain and there's a monastery, a very famous one. And the mountain is 1,000 meters high and the monastery is close to the top. So we thought that is a good place to put our plants there. And why we did put it in a monastery had nothing to do with religion. We put it in a monastery because the animals would eat our lettuce if we would put it outside or somebody else would destroy it. So the monastery was basically a guarantee that the experiments go until to the end. And on the ground in Lleida, which is a city next to Barcelona, we had growth chambers and we repeated the experiment. So the physical twin sender is a mountain, the physical twin receiver is a growth chamber. This gives you just some information on this very famous Abbey of Montserrat near Lleida. And you see that it's in a place where you can expect extreme weather conditions. Now we use this Italian lettuce variety because I was told this is very tasteful, this is very common in real case cooking. So we thought that is a good choice. And we made 4 kinds of experiments and we repeated it 2 times. So you see 2 images. One experiment is we watered the lettuce sample in soil. One experiment is we didn't water it. And you have to know in summer in Lleida and Barcelona, it's 40 degrees, so you can immediately see the outcome of that. In one case, we watered, but we gave 50% sand because now we also work with Regolith from Exolith and another company from Florida. But here it was sand, but we thought it's some kind of analogon. And then we gave fertilizer to it. In the other cases, we didn't add fertilizer, but naturally there's some fertilizer in the soil mix. We also did do hydroponic experiment in the growth chamber, not in the monastery. And we repeated the soil experiments in the growth chamber. That's what you see here. Now, when you look, we made an experiment for several weeks. You see here the humidity and temperature. What you can immediately notice is there are 3 periods. Yeah, at the beginning, left, you have high humidity. In the middle, you have low humidity, and then you have high humidity again. And so is the temperature. The temperature is antagonistic. At the beginning, it was relatively low for the region, then very high, and then it was low. Now, question is, how good can we reproduce the temperature? And you see here that was quite reasonable. You have to know my group is poor, so we had to do everything by hand. So the student has to change the temperature every hour or every half hour by hand. And in the night, they could naturally not change it because they had to sleep. And also at the weekends, there were limitations. So within the severe limits, which we don't have now anymore with our big center, within the severe limits, I think we managed quite well to get the temperature in the growth chamber. So we brought weather in the growth chamber. Now, I think you all know the lettuce grows quite linearly. That naturally depends on the way you grow lettuce. This is a hydroponic system, and there are also periods where lettuce does not grow linearly. So we should keep that in mind when we see the results. Here you see the two physical twins. You see the match of the temperature over weeks, but you also see it within one day. That's on the right side. And you see the yellow one, that is the night. And you see at the beginning of the night, because there was no control anymore of the students, there's difference. But at the end of the night, our growth chamber is quite the same as the temperature on the mountain. The big thing which we have not solved, but which we want to solve now, is humidity. We could not control humidity. It was fixed in the growth chamber. It fitted well to the beginning and to the end, but in the middle, we have this period of very low humidity, which we could not match. We have also soil sensors, but we didn't fully exploit their potential. Now we will use machine learning modeling. Remember, we have 4 experiments, right? We had water, we had no water, we had this sand and soil, and we had the fertilizer. They are all given here, and then we made it 2 times. Yeah, that's why we have 8 experiments, and GZ stands for growth chamber, while M stands for mountain. And then you see that the model is partly valid. The first result we ever did, so we could not expect more, is partly valid for the watering situation. Not to surprise, it's not valid when we do not water, M3 and M4, M5 and M6, partly valid with the regulate analog. And when we add fertilizer, it's not valid, which is very clear because the model does not consider the addition of a fertilizer, and similar conclusions you can make for the growth chamber. So we had a first kind of experiment. What we also saw is that on the mountain, we have much more biomass, that's the blue points on the left side, than in the growth chamber, which is the red points. Actually, it should have been the same, but obviously the pot size and other conditions like the sun shining instead of LED made a difference. On the right side, you see the growth in the hydroponic system, which I don't want to further comment. Now, knowing this, knowing our fit was not very well, we thought we have to go a bit deeper into modeling, into algorithms, into regressions, and into data. And this will take us the next 10 years, as I said. What we do use is IoT data by sensing. We use also historical data from the region of the physical twin. But then we thought, in a way, the climate in Spain is the same like in Arizona, or similar, not the same. So we can also use data from Arizona or similar desert regions, and that is what we do above. So we use historical data from region of similar climate, and sometimes we use 3 or 4 regions together, as you will see in a second. What we just started to do recently in the last 2 weeks was we use historical data, but we mix them with best practice data. I will explain what that means. It cannot be understood now, but I will explain it at the example. Now, if you look, we started with Spain. Yeah, so we started with historical data, the region of the physical twin. And here you see over the years how much lettuce was produced, how the temperature is, and the humidity. That is quite well defined. So that was of help. And when we looked for the model validity, it was actually good. And it's in almost all cases good, which we will see. But that does not necessarily mean that the model is very good in predicting the biomass outcome, as you will see in a second. Now, here we show which historical data we used in concrete. There's this IDIS cut experiment. We used it, and this is the Italian lettuce which we used, the lettuce Maravilla de Verano, and we also compared it to Romaine lettuce, which was also grown in the Spanish region. Here you see for the first time fit values, so this R square values, which ideally have to be 1, and you see some of them are quite close to 1, as said before. Now, because we want to go further, we also considered regions in US, the desert regions in Arizona or Nevada. They are arid. Spain, I would characterize as semi-arid. And below you see, in terms of temperature, sunshine, humidity, and rain, similarities, but also differences. And we also considered tropical regions, which are in temperature quite the same, but naturally differ much in rainfall. We used similar, different regressions. It was natural to start with linear regression anyhow, but also since the lettuce grows linearly, but we have also other type of regressions which are named here, and we use them for the Spain and US data. So when we did this all, the final outcome of all the experiments which you see here was that it was actually not better than before. So the use of more advanced regression algorithm models didn't pay off, and the use also of more historical data from other regions, at least here in this case, didn't pay off. But what we saw was also that water samples, soil and sand samples can be, by order of magnitude, reasonably predicted, although we have to work a lot on the precision. Now I come to the second study, and then I will be at the end. Now we made an experiment which is physically not possible. We growed lettuce in 1 week in Lleida in Spain. We growed it in Argentina, in Singapore, Adelaide. And we also growed it in Fairbanks, just to cover all the climate zones. And that study relates to climate 2050. So we have even a polar climate zone. And that was possible because we did it in April when Fairbanks was reasonably warm. Here you see the temperatures measured in the 6 cities, and you see directly one is different to the other. That's Singapore, number 5 week. Singapore is always hot, has low variation between night and day. That is very visible. To our surprise, the other 4 cities, 1 to 4, were pretty much the same. It was cold in Paris, colder than expected, and it was warmer in the regions in Argentina where it was winter, and it actually was also warmer in Fairbanks than expected, but okay, that is weather. You cannot plan it. Here you see how we tried to match the temperatures in the growth chambers. It's not perfect. There are also deviations, and there's always a reason on that. But all in all, it worked quite well. Now, when you look at rain, it's interesting, and that is maybe also global warming. In the period we looked at, it rained only 3 times in the city. So over a period for more than 1.5 months, there was only 3 times rain, and 1 time was very little. So that says also something about our climate change, and that naturally was not good for the growth of the lettuce because we followed the data of the rain. Now here's what we got out. It's the same experiments as before: watered, non-watered, fertilized, and 50% soil and sand. You see there's quite some linear growth, but remarkably, the last 2 weeks, weeks 5 and 6, it always shoots up. Sometimes more, like with the fertilizing, sometimes less, but it's visible in all the plots. So a deviation from the linear plots. And interestingly, the biggest jump was made in Fairbanks. So in a polar region where you not necessarily would expect that it's good for lettuce growth, at least to our experiments, that was very positive. And this is maybe something why we do space experiments. Nobody maybe would go to Fairbanks and look if that is beneficial for lettuce growth. But this space experiment shows that those temperatures with the other conditions might be beneficial. Now, we looked on first modeling results. This also shows the linear growth nicely in the first 4 weeks, and then it shows a jump. Also, there's no increase between week 5 and week 6, but at least the trend was confirmed. And as we see before, the model is still not exact. We are just doing this since 1 year. And but the water situation and the soil and sand can be better predicted than the other scenarios. So that is what we have seen also before. We tried some more advanced regression coefficients. We come even to an R2 square of 1, so the ideal situation. But as I said before, that doesn't mean that the prediction is ultra precise. And I could quote on the reasons for that, but there's not time now in this lecture. Maybe if we make question. If you remember, there was a second approach. We take historical data here from Malaysia, and we add what I say best practice data. So it's known that lettuce for 1 kilogram needs 237 liters of water. So we put those data on the right side under a virtual rainfall. So this is not the actual rainfall in Malaysia, it's much higher. So we said, so we wanted to combine this and see if we have a better fit. And indeed, you see the fit of the model gets a bit better than before. Yeah, the model is on the left side above. And then we have the 3 experiments. The unwatered situation is not given. And you see there's a linear growth, which we have these dot points, the blue one. And then always in the last 2 weeks, there's an increase, smaller or bigger, which I made with the red dot points. Finally, I'm on the very last slide. We make a digital twin model with the group of Sigfredo Fuentes in University of Melbourne, and this is all about aroma. We have shown in 5 papers that you can change the aroma in space with the group of Ian Fix from the University of Nottingham by plasma cleavage. Meanwhile, we do it by enzyme cleavage. And we approach here a much more complex problem of a digital twin. This is how people in a share, in a microgravity share, experience the flavor of food. And we use farm bots, which we have on the Adelaide side and on the Melbourne side. Finally, we work with XM Pro. This is an Australian US company on digital twins. Here, just to give you an idea what can be done with a professional software. Before, we just use the free available Microsoft versions. So probably with this software in future, we can do much more. And you can hear this is plug and play, a no-code software, so which people like us who are not computer engineers can use. Now I'm really on the last slide. I would all invite you to contribute to this special issue in the International Journal of Molecular and Physical Gastronomy. I'm in the editorial board of this journal, which is operated from France. You see some of the guest editors who come from the food science. And we started here a contest on the space dishes, so people to imagine a space dish and to give reasoning why this is a space dish. No experiments are needed. This is all on imagination. And we will conduct here several papers, and they will go into international food contests, and you can get some more information about this. I call this the Space Cookbook Challenge, actually. Yeah, okay, we have an artist, as you've seen before. Space has to be visualized, and this is the space microfluidic plant on Mars. Thank you so much for listening to me. I see quite many people are there, so I'm not sure if we give questions, but if there are questions, I'm happy to answer.
All right. Thanks a bunch, Volker. That was quite a talk. You really spanned a lot of subjects. It's great to hear that Plants for Space is being so productive and so active. Thanks for the updates. Um, We do have a couple of questions, and I'll just jump in. Uh, Oscar was curious about the light levels between the twin and the chambers, or the regions compared. Specifically, he mentioned that PPFD is a strong determinant of yield.
Which kind of levels can you say again? The light?
Yeah, I guess the light levels between the digital twin and the chambers, like were they the same PPFD, I assume is the question.
Ah, now I get it. Sorry. It's a very good question, and I have to admit, we just stepped into it, and it was probably not the same. We used the existing LEDs in the crow's chamber, and on the mountain we had the sun. We put the samples, the pots, in a position where they had shadow over day and sun, because in the sun they would have been completely burned. There's so much to be improved, and that is the reason why our model does not really work very well, but we want to do that now much better.
Sure. Um, Kevin asks, he says, I understand your nutrient model is based on plants grown on Earth, but do plants produce different nutrient quantities in reduced gravity or hydroponically or in regolith?
Yeah, probably they do. I mean, human digestion is also different. The medicines with human work different, so probably it does. So I think this is also a degree of complexity and curiosity, which I like to approach. And I work with Rafael Loero, who does a lot of regulate research. We do also on our own. I've not shown this today. So I think there are fantastic opportunities. We just started. We like to do this exactly in this direction.
Hmm. Um, Okay, there's some pretty good questions coming in. I like this one from Marshall. Just to clarify, what benefits are offered by the digital twin approach? Is it the delayed experiment, which is facilitated by the digital system? Or like why is it better than just doing a regular analog experiment?
Yeah, the normal digital twin experiment is bidirectional. Yeah, what I have presented here, honestly, is more like a digital shadow, as it's called, or this digital model. Um, we are now underway with the XM Pro software to make a bidirectional communication, and that means the data come in as it did with us. And the model is automatically created, and then you use this multi-agent system. So, like 10 experts sit together in a room, like here now, and the 10 experts decide how the plant has to be changed, the hydroponic plant, for example, to give a better result. So that is a real digital twin. Yeah. What I've shown is, as I said, only a digital shadow. And on top of that comes with my model that if you have two physical twins communicating with each other, you can bring in experimental condition in an ideal containment. Yeah, the growth chamber is considered to be an ideal containment, and you can study the conditions under better conditions and also with higher replicability. Because that is what I noticed with my ISS experiment. I would have loved to done it 10 times, but I could not do it 10 times. There was only one time.
Hmm. Hmm. Yeah, that makes sense. All right, here's one from Ben Sykes. Within the context of multi-trophic interactions, do you feel like plant microbiomes or fungi and bacteria are drivers of distinction between some of the twins or are implicitly incorporated? And is there value in modeling them as distinct elements or I guess agents in this example?
Yeah, the answer is a good question. The answer is clearly yes. I think the next talk or the second next talk is about converting the dead regolith into a living soil with microbiomes and all the bacteria which usually are there. I think that is a very valid research direction, which we also do. There are initiators. So there's a lot of plant regulators. So there's a lot of agents besides nutrients which help plant growth. So I definitely think we have to have a look on that.
Hmm. And Ben had another question about, I think, one of the earlier slides when you were comparing the root system of the different plants. He wanted to know if the area was 2D or 3D, I guess, because it's hard to compare something like a sweet potato root to flower roots like poppy.
So was a question to my first slide with the three-dimensional fertilizer network, because that is three-dimensional.
Um, I guess, oh, I think it was more about the roots rather than the
Yeah, yeah.
nutrient delivery system. Just how do you compare, uh, you know, plants like sweet potato versus plants that don't have tubers?
Um, that's probably a very interesting question, but I have to admit that I'm not a root expert. We work with the University of Nottingham with Swan Rarup, who is a root expert, and my student will go to him in April. So, but sorry, I cannot answer this question.
That's all right. You're in the hot seat. There's a lot of tough questions today. Okay, let's see. We still have a couple more. Um, Matthew Lynn, how did you simulate microgravity and cosmic radiation when growing lettuce? I'm not
Um,
sure if this was a.
we did it, and we have a nature paper underway there, but this was not given here. We have a microgravity machine, the random positioning machine
Mhm,
2.0 from Airbus, which you all know, and we operate it in the RPM mode, we operate it in the Kleinostat mode and in self-program RPM mode, and we have learned a lot about shear forces in fluid, and we have an own paper underway on this. So we all know that it's not so easy to fully ensure that you have microgravity under those conditions. The cosmic ray, we have the Bell Laboratory in the Prague building, and this laboratory has alpha, beta, and gamma radiation, and people who work also on space, so who have a good idea how we can simulate space conditions. The problem is usually that the radioactive sources are too strong, and anyhow we cannot make a 1 year experiment. So we usually work at similar doses, what means the experiment is much shorter than in space. Yeah, might be 1 year ISS experiment. We make a 1 hour or 3 hour
mhm.
experiment, and then we make it at a much higher dose rate. But we have those facilities. Naturally, this is not like Brookhaven National Laboratory, who can also combine everything and make cosmic rays. But within our possibilities, we are quite happy to do this. And my experience was, by the way, that the plants are pretty tough, maybe tougher than humans. When we bombarded them with alpha rays and gamma rays, which were really high, they survived until a certain level where they naturally then broke down. But they were pretty tough concerning those rays.
Yeah, I think humans are definitely going to be the weak link in these closed systems.
Yeah, that's so.
All right, Volker, one last quick question for you before we move on. Um, you described quite a lot of the stuff that the ARC Center for Excellence Plans for Space is planning to do. Tell me which project is your favorite? What's the one you're most looking forward to?
um, yeah, okay, you ask a polymer scientist. So, especially in Adelaide, but also with the other partners, we want to have plants which make bioplastics. I think when you talk to the public or to a journalist, that is maybe something which is not expected from
Mhm.
general public. So I find this very interesting to program plants to make medicines, which we do. Um, that is maybe still understandable, seeing that plants make nutrients, but that they really can produce bioplastics, which you also need in larger amounts. I find this pretty challenging. I mean, the overall idea that a plant can produce everything what you need. That is a challenging idea. Nature does it, but yeah, we were stuck so long on petroleum and natural gas. So now finally we come back to this concept.
Yeah, absolutely. It's nature's toolkit. Uh, well, Volker, thank you so much for this presentation and for your time. I appreciate you staying up late to tell us what you guys are working on. So I think we're ready to move on to the next presentation, which is going to be Michael Gildersleeve from Interstellar Labs, who is telling us about nucleus.
Thanks so much, Patrick. Can you guys hear me all right?
Yep.
Okay, good. I'll just share my screen. Is that looking all right?
Yep, absolutely.
Okay, great. Thank you. Hey everyone. Thanks so much for having me. My name is Michael Gildersleeve. I'm a plant scientist and the mission manager at Interstellar Lab. Today I thought I'd tell you a little bit about our nucleus system, which was developed for NASA's Deep Space Food Challenge, and share some of the results, especially from the ground testing that happened at Ohio State University for 6 weeks during phase 3 of the competition. A little bit about Interstellar. We're a biotech company founded in 2018 by our CEO and founder, Barbara Belvisi. Terrestrially, we build CEA systems for the purpose of producing plants high yielding in secondary metabolites or any other interesting compounds to our customers like L'Oreal or Robert Tet, mostly in the cosmetic and perfume industry. We identified some of our space goals on the space side, generally being helping address developing systems to minimize resource inputs while maximizing outputs, increasing diversity of food produced and the nutrition from that to help sustain long duration space missions. And this seemed to be really aligned with the Deep Space Food Challenge. So we submitted to that with Nucleus here. Nucleus stands for Nutritional Closed Loop Eco Unit System. I did not choose the name, but yes, it's made up of 6 food production quarks we call bioquarks, or food production modules we call bioquarks, which are capable of producing food products from plants, fungi, and insects, as well as 3 subsystem modules, which we call system quarks. We see the applications of Nucleus as both a research facility and a food production system. Conceptually, the system is meant to be its own closed loop ecosystem where resources and nutrients are exchanged between different species. And to be able to quantify that would enable opportunities for space ecology research, plant research, mycology, and entomology research. As for the food production goals, it was designed to address the known nutritional gaps in the astronaut diet and to increase general diversity of the food products offered. As a life support system, we see it contributing to food production, of course, but also air revitalization, water recapture, waste management, and the regeneration of the biological inputs to the system. So yes, it was submitted to phase 1, 2, and 3 of the Deep Space Food Challenge. Just this past August, it was chosen as the winner, which we're super grateful for. The goals of the challenge were outlined as helping to fill the food gaps for a crew of 4 for a 3-year round trip mission with no resupply, and terrestrially to build a system to improve accessibility in food scarce areas on Earth. Also to achieve the maximum food output for minimal outputs while generating minimal waste. as well as to produce a variety of food options. And so this is us with the team here at The Ohio State University doing the ground training for the Simunauts. So the nucleus is currently TLR5 with a production area of roughly 2 square meters, but production volume for some of the species is a bit more relevant. Here's the power and telemetry laid out, and the environmental controls being temperature, BPD, humidity, CO2, lighting, airflow, as well as exchanging gas and resources between the different modules. So BQ1 all the way to the top here, this is for large plants. We call it the veggie cork. And for sprouts here, so there's a bit of at the time, there's a bit of confusion, the difference between our sprouts and microgreens. They're exactly the same system, but one is just grown without the use of any artificial lighting. BQ3, our mushroom cork, another veggie cork, our microgreens cork, and the black soldier fly larvae cork, which is the insects we chose. And for our system corks in the middle, here's our electrical cork, our HVAC system, and our fertigation. And this is a bit of the outline of how we want the system to work, with exchanging the oxygen from plants to fungi and insects, and the CO2 generated from the fungi and insects back to the plants, recapturing transpired water, putting that back in the fertigation tank, and taking the inedible biomass from the plants, feeding it to the mushrooms and insects. Same thing with the mushrooms, the spent substrate going to the insects, and then the frass generated by the insects as a addition to the fertigation, with about 95% water recovery. And we wanted to design it to be easy to use. So we have this custom application used to control and program each of the corks, which you can program all the different environmental parameters, allowing you to support for a range of species. Of course, during the competition, we had our own ground control answering all the Simunauts questions the whole time. Here's some of our crew time data from the mission. Most of the time spent was planting and harvesting. We really wanted to capture this data because we wanted to make sure we were automating the right tasks, and not automating tasks that crew would enjoy doing, like harvesting. And some of the survey work we did after the mission definitely supported this. So we're happy to see that. Here's some of our inputs and outputs data. Total biologic inputs were about 10. The output was about 10 kilograms as well. This gave us an output to input ratio of about 1. With some mission anomalies, we weren't able to grow any mushrooms, so this brought our ratio down quite a bit. But we estimate a food output of about 150 kilograms for a 1-year mission, and that's including regenerating the biological inputs. So going seed to seed, the plants, creating spawn from the mushrooms, and rearing the black soldier flies as well. Here is some of our nutritional data. This was just what was generated in the 6-week mission. Obviously, it does not fully cover all of the base needs of 4 crew members, but it did so in some areas, and we are happy to see it as a good supplement to the existing, what would be the existing astronaut diet. We had also developed a food safety plan, a HACCP plan, and yeah, this was a new process for me especially, and so yeah, this was something we worked on a lot, and we'll definitely continue working on to make sure that the pick and eat foods are all safe, that everything is processed in a way where it's safe for anyone consuming it, and would be so in space as well. And yeah, as for our dual terrestrial and space kind of business approach, this is kind of how we see it working on our both terrestrial and space side of how we build the CEA facilities that then the data we get from extraction and analysis, we build our bio library that better informs the environmental parameters that would steer plants and species towards producing these. And it's a continuous process that I guess iteratively refines itself. Yeah, and our next goals for the nucleus system, I guess, would be to take a single quark about the size of 1 or 2 MLEs and start our LEO experiments and testing. And that is all I have. Thank you.
Okay. Thanks so much for that, Michael. I visited in your facility in Paris a couple of years ago to tour Biopod. And I've been following the Deep Space Food Challenge and Nucleus really closely, so it's awesome to get some more detail. Um, I really love how, everyone can visualize the diagram of the closed food loop system with the mushrooms and bugs and plants and stuff, but almost nobody ever puts it into practice. So it's really fantastic to see what that looks like, and also to hear that it's been so successful for you guys. Um, so while we're waiting for the questions to come in, I've got one, which is I've actually got a bunch, but I have to share the questions with
Please.
everyone else. So uh, first, I want to know about the insect frass to fertigation loop.
Mhm.
How did you guys do that?
So this is not something that was put in practice for the 6-week mission.
Hmm.
But this is something that we're definitely still currently working on. We tried, I guess, just so this separation of the frass is its first problem to tackle, I guess, and that went pretty well. Taking that frass and then processing it in a way to put back into the fertigation is something we're definitely still working on. We think it would be best to incorporate some sort of bioreactor using the frass, and then turning it into something that's a better additive to the fertigation.
Okay,
But right now, this isn't so solved, I would say.
sure. Um, okay, it looks like I can't selfishly ask all my questions because there are a lot more.
Okay.
The Amanda Stockton wants to know, the food production was for a 6-week period, and how would that scale for continuous use? Like pepper output would probably go way up if it was a longer duration.
Yeah, so that's oh, and I wish I had some other graphs on here, but that's where the figure of 150 kilograms for a
Mm,
year of production goes. So as time goes on, the input to output ratio just keeps, or the output to input ratio just keeps going up, right? Because you take your initial inputs, and then over time, as they're regenerated, right, you still have that constant of that initial input, but then the inputs are regenerated over time. Um, so as for the food production part, or total food production, I guess, um, the more time that, what am I trying to say? The over time, I guess, it's dynamic in the way that you need to now schedule time to go seed to seed or to regenerate spawn. So incorporating that, you see kind of like a dynamic equilibrium of the general food output as it goes on, but then you need to schedule in regenerating inputs.
Yeah, that makes sense.
That makes sense.
No, it does. As a general reminder to people, if you're not a panelist, try to put your questions in the Q&A so they're easier to find. I had a question, I think, which matches with Don. What were the CO2 levels in the mushroom and fly quarks? Because for oyster mushrooms, Don says they're not very tolerant to high CO2, which is needed for plants. So that's something your HVAC was working with to deal with? Or?
Yes. Yes. And as I mentioned, we did not get oyster mushrooms during the mission. And so they definitely are very sensitive. And with a small volume of these modules, I think it got up to the highest it got up to is maybe 6,000 ppm. And with the certain plant variety, at some point when the plants got large enough, they were started to assimilate carbon at a rate that was able to match it more. But yeah, we think the high CO2 was a part of the problem for the mushrooms.
Were you dosing the CO2, or did that just come from the bugs?
No, all the CO2 came from the fungi and the insects. Yeah.
But there were no fungi because of the CO2.
No, well, the mycelium was running rampant, producing a bunch of CO2, but no fruiting bodies. Yeah.
Okay, got it. All right, that's pretty interesting. Joya asks, what was the biggest challenge in implementing Nucleus?
That's a good question. I guess part of the challenge was, I would say, training. Having worked on, the concept and the physical system for maybe 3 years, right? The whole team is super aware of all the little quirks of the system and how to use it, and then translating that to someone like the Simunauts who are first time users. It was definitely a good practice in communicating and teaching when maybe you don't know the best way to say certain things or to teach certain concepts, I guess. That was a challenge, but a very rewarding one as well. And then just generally getting the system to function as we wanted is always a challenge.
Sure. As a note, you might have figured this out already, but Don says he's pretty sure he remembers reading that oyster mushrooms just won't fruit after 2,000 ppm of CO2. So that definitely could do it.
Definitely was part of the problem. Yep. And we were all remote, right? So we're playing mission control and trying to figure out why this isn't going on. And I'm seeing these CO2 levels, skyrocket. I'm like, guys, I think this is the issue.
Yeah. Jane has a good question. Are there plans to extend this to be like fully closed loop by recycling human waste as well?
My personal plans or the company plans, because this is something I've always been super interested in, and personally would I guess I wouldn't say do my own projects, but it's something I'm trying to pitch and think would be super useful. I have another schematic trying to include the human in the loop, and I think it's the future. I think it's exactly what's needed, but yeah, it's hard to sell that to especially when you have to produce food safe or you have your HACCP plan and you're trying to incorporate something like this. It's not so easy.
Yeah, definitely. As a side note, you might have missed it, but one of the speakers yesterday had black soldier fly larvae in his toilet system that was working towards compost. So I don't know about the HACCP. I don't know how food grade it was, but yeah, definitely possible. Good to know you guys are exploring those options. There are actually a ton more questions. Maybe you can look through the chat and answer some of them. But we're going to have to
Sure.
move to the next presentation here. So thanks again, Michael. It was really
Thank you.
fascinating. Yeah, so next up we've got Adam Williams, who's going to tell us about regolith to soils, transforming lunar regolith. Hey, Adam.
Hey, good morning. Can you hear me?
Yep.
All right. And is that sharing?
Yeah, we can see it.
Okay. Good morning, everyone. Thanks for having me. I'm here to talk about my PhD research at the University of Minnesota, where I am focusing on transforming lunar regolith into agriculturally functioning soils, or at least working our way there. Background, I work as an engineer in space technology and other kind of complex R&Ds. I have degrees in economics, software engineering, bioinformatics, and computational biology, a certificate and a master's in space resources, and a current PhD student. But I'm really just an aspiring moon farmer. I also serve as a space ambassador for the Space Society, so shout out to the National Space Society. Really, when it comes down to it, my research goals are to characterize the methods to transform lunar regolith into a soil to support off-Earth agriculture. And I can categorize this in kind of four primary areas: biological change, chemical change, physical change, and structural change. And really, food is the gating factor for the habitation of space. I don't think I really need to convince this audience, right? But humans are chemical rockets in many ways, and we'll need calories to support any activity out there. And my goal is to solve or at least partly address this using lunar resources so we can separate ourselves from Earth-based supply chains and do so in a regenerative way, leveraging biology that can ultimately dovetail for improvements back to Earth. And by overcoming these challenges, we can see general improvement to systems really back on Earth here, dealing with pollution, radiation, developing closed loop systems, increasing soil health, and so forth. So really, primarily what I'm trying to do is take this stuff on the left, right, the lunar soil, and turn it to something on the right. And it may not be immediately obvious, but the underlying rock types that we find on Earth, particularly in tropical zones, are very similar to what we see the primary basalts that form the lunar surface. So if we can see tropical zones, which are sometimes some of the most productive areas on Earth, how do we drive that change and do so on a timeline that is useful to us for space exploration? Primary types of rock on the moon. There's the highlands, which is, look at the moon, there's kind of the white area and the darker area. Highlands is plagioclase, feldspar, olivine, and pyroxene. The mare is also these same rocks, mineral types, but much higher in pyroxene compared to the plagioclase, feldspar of the highland areas of the moon. We look at mineral weathering. As I mentioned, there's essentially plagioclase, pyroxene, and olivine in the highlands. And then the mare has the plagioclase, pyroxene, much higher in pyroxene, olivine, and then some areas are high in ilmenite, which is a very titanium-rich mineral that some are looking at to use for production of metals on the moon. That being said, if we look at this figure on the right, we can see mineral weathering pathways. And while I don't really know where we'll end up, I do know that things on the right tend to be better for plants than the primary things we see on the left. So my research is really trying to ask, how do we drive that into, how do we make a feldspar into a smectite or a clay type mineral quickly instead of on geologic times? There are some questions when I present on if we can even grow plants on the moon. I don't think I need to convince this audience as much, but there was the University of Central Florida where they grew plants in actual Apollo samples. In the 70s, in the upper right, we can see plants were grown with some of the original Apollo samples. They were found to be safe. There was speculation that the moon could somehow be toxic or something like that. It was not. And then the Chinese Chang'e 4 mission down in the bottom right, we did see sprouting of cotton plants, and it grew upwards. Didn't last very long. It didn't have survive the night capabilities, but was sufficient enough that plants 1/6 gravity is enough gravity for a plant to orient itself. Though we've already seen on the ISS plants can do fairly well in low and microgravity conditions. I'm not going to spend too much time on this chart, but really what I'm trying to do is compare soils to regolith and drive regolith in ways closer to soils, right? So regolith lacks aggregates. It behaves very strangely in water. It tends to hard pan and lock up. It's extremely hydrophilic. It has very low cation exchange capacity due to lack of clay minerals. Any nutrients in there are essentially not made bioavailable yet. They're locked up in the rock. Organic matter is basically absent. As far as we know, there's no microbes or fungi on the moon, though I have my suspicions there may be. And then the pH range is ultimately tolerable within Earth conditions because it is in many ways the exact same rock we find here on Earth. But to move it into a soil takes a lot. That leads me to kind of my first main area of my research, which is the exploration of earthworms and their impact. So I characterized earthworms on both Mare and Highlands simulated regolith using X-ray diffraction, extractable water extraction for element availability, cation exchange capacity analysis, and other soil testing, bioinformatics, pH, and electron microscopy. It's 3 types of worms. Not going to get too much in here, just the time limit. But worms we move through the soil, cycling minerals and changing the structure. It took a while to get a successful worm habitat going. The regolith itself is, if it's dry and touches the worm skin, it will desiccate the worms and suck out all the moisture. Worms breathe through their skin. So getting the right ratio of organic matter to hydration levels took a lot of trial and error, but we've ultimately got it nailed down. We had some success here with Lumbricus terrestris. Those are the really big earthworms. These struggle to be cultivated commercially just on Earth normally, but we were able to see just within 11 days the worm being able to break through this regolith manure mixture that I tested with and develop a habitat. We've been in this photo, if you can see, there's a black coating suggesting that the worms are creating burrows and that type of things. But we ultimately moved more to Essenia fetida. That's the common red wiggler or composting worm that most people are familiar with. And here's just an example of what happens in about 30 days or 31 days. So on the right, this is day 5. It's 200 grams of media, about 70% regolith simulant and 30% organic matter. The paper on the top is to simulate leaf litter. I found that greatly improved outcomes as that's part of the worm's daily life cycle is to kind of move up into the leaves and down. Also gave them a place to escape. But you can notice that it's very hard here. When you add the water to this mixture, that hard panning effect takes into place. But over the course of the days, the worms are able to infiltrate the media. You can see the castings forming here on the surface as the worms move through. By 2 weeks in or 18 days, the worms can move through the media very successfully. And then by 28 days, if I didn't tell you that was simulated moon dust, you probably wouldn't know that that's what it was. Here's with Mare type as well. We see similar improvements, right? So here's what it looks like unwet. 24 hours later, you can see it kind of hard pans again. But within a few days or a week or so, the worms are able to infiltrate the media. They're chipping away at it. They're consuming the organic matter in there. By day 30, they've worked through everything. Somewhere in there between day 30 and day 45, you start to get that soil smell, right? So if you know that after rain kind of smell starts to come off, showing that the media is very alive and bioinformatically rich or microbiologically rich and very active. By day 72, it's worked over. You can see that the color has changed as well. That's not an artifact of light. It gets much darker. This is consistent with the research that Carpenter et al. Did, which is somewhere around between 30 and 60 days, the chemical structure of the minerals starts to change. So we see just observation of biological change, structural change, right? And by day 85 or 100, that looks like potting soil that you'd get out of a bag. I did see worm reproduction in both the Highlands and Mare during my experiments. So this is a good sign for a long-term sustainability and maintainability of such a system if deployed off of Earth. And here's just some electron microscopy images just for perspective, right? So we can see here the Highlands, the Mare, and a normal earthworm casting. You can see that particles are quite jagged and sharp. This is because they are unweathered. and this is one of the primary reasons due to the strange behavior. But we can see here the moray, even just within a day, they are producing castings. They are forming these minerals into something that we were more familiar with. We can see here organic matter is being embedded into these castings, so they're able to pull it out of the media and consume it. By day 4, you can see large amounts of little bits of organic matter here inside the worm casting. If we zoom in on the grains as well, we can see a rounding effect. This is somewhat subjective. I'm working on trying to make some sort of more formal statistical analysis, but it's consistent with the research that Suzuki et al. Found, which is that within very short amount of time, the worms have a gizzard, and they will grind the particles inside their guts while they're digesting, and that rounds the corners of these grains, weathering them physically very quickly, and ultimately getting that desired change. Yeah, and by day 7, we see large bits of organic matter being included here into these castings and being formed together. We did some spectral analysis just to kind of prove that that thing that looks like a stick is in fact a stick, and the things that look like regolith were regolith, right? But it's showing that these things are coming together and happening. And by day 30, right, we can zoom in on these particle grains, and they're incredibly smooth compared to those sharp, jagged edges of the original raw photos I had shown just a little bit ago, which ultimately gives much better outcomes. In terms of pH, worm castings are pH neutral. The literature suggests that the worms don't have a huge impact on pH, but we do see a general trend towards a pH of 7 over time, with the highlands kind of slightly drifting up, though it's near 7 anyway, and the moray type coming down from kind of an 8.5, drifting down more towards an 8. You don't have to read all this, but we did total carbon, total nitrogen, and cation exchange capacity. And basically, for the summary for this is that nitrogen, the dishes that had worms in them held nitrogens better, even though they did see a nitrogen loss over the 31-day experiment. But we saw a significant increase in total percent carbon in worm dishes. And perhaps the most striking finding is that the worm dishes improved cation exchange capacity nearly 25%, with some dishes being much higher, as we had a statistical outliers, right? So if we just compared here at the bottom, right, dish 18 versus 38, right? Dish 18 was nearly 26 and 38 was 19, right? So, but on the average, it was about 25%. So a much significant increase in the ability to hold nutrients and other ions within the media. Moray, we saw very similar things around nitrogen. In the moray type, for whatever reason, both saw a loss of carbon, but the worm dishes saw a much better retention of that carbon. And again, we saw about that 25% increase in cation exchange capacity. Working on processing these results here, but we've did extractable elements to see if these elements were becoming freed by the worm digestion or some other effect. That data is still forthcoming. We have also the spectral analysis, similar to Carpenter et al. They did it without just a northite, which is really the same thing. And they found that within 30 to 60 days, a northite would start to see chemical weathering. So you can see a shift in these spectral peaks here. I don't have all that data ready here for my experiment, but I can tell you that I seem to see the same type of thing, particularly with the 30-day or so experiments. So the farther along dishes. I'm also doing bioinformatic analysis. We have that data back. We can definitely see, haven't completed all of it, but we definitely see an explosion of microbial communities. I'm hoping this will serve as a source of interest for the community at large, just to help identify potentially interesting microbes or fungi. For those interested, we did ITS for fungi and 16S for microbes for bacteria. And then I have also done some preliminary plant trial experiments. This is kind of the latter half of my PhD. I'll do some more detailed ones, but we participated in the Plant the Moon Challenge this spring. I focused on dandelions. I think dandelions are a really interesting crop for use in space. They're tenacious, they're perennial. They produce a flower that's familiar and well-liked. Every part of them is edible. Their roots are known to have medicinal properties, and there is outstanding research that you can use them as a source of rubber. So that's potentially an interesting application as well. And they're useful in salads and that type of thing. Don't have too much time for it, but basically the summary is the dish with the worms in it grew better than every other dish combined. That was how dramatically more effective the worm dishes were. You see here on the right, we can see a dish with a worm. We have very well-grown root structure all over the place, very healthy-looking leaves. The middle was just raw simulant. We can see that it's short on some sort of nutrients that's causing probably phosphorus and nitrogen. Its roots are extremely anemic in their length and size. On the potting soil, which was more like a pure compost, it also didn't do very well, which was kind of surprising. It suggests that dandelions like more minerals and can't just do organic matter. But the organic matter mineral worm enhanced media was very successful. Here's a look at the root structure for those same images, right? We can see this root mineral interface. The shape of the root is very healthy looking instead of the stunted or kind of depleted looking roots. So yeah, I'll just be continuing this research through my PhD over the next couple of years, but we'll continue to characterize these areas. There's some intellectual property around it just for disclosure for my research. I'd like to thank my team, my advisor, Si Young, and then professors Yu, Ishii, and Bailey, as well as Christina Ting and Tyler Baum, who have been helping with the research as undergrads and master students, and thank my funding sources as well. With that, I'll try to handle any questions.
Wow, thanks for that, Adam. That was fascinating. It kind of looks like you've solved the whole regolith to soil thing in one fell swoop. Really impressed. I'm going to abuse my position here to show you my worm and regolith thing really quick, if you don't mind. I
Sure.
think you have to stop sharing though. There we go. Yeah, check this out. I did aquatic worms though, and I just put them in a jar with some regolith and a little bit of aquarium water, and I found that these detritus worms totally integrated all this organic matter into the regolith, and like you can see horizon layers of soil starting, well, of organic matter starting to form, like putting the mulm down into the regolith. I haven't actually done any analysis on it yet, but pretty similar results to you, interestingly.
Yeah.
So I guess now I'll ask the questions from everybody else. So did you analyze how worms did change the release of nutrients like potassium and phosphorus from the regolith?
So we did. I have to go back here. So did we did do potassium and phosphorus. So I don't have that data just yet. I'm still working through the statistical analysis, but it will be in the water extraction job. So it should be in the final paper, or I'm happy to look into it a little more and consult or work with y'all.
Okay. Did you mention specifically what regolith simulants you were using?
So I used Exolith Labs, just they're available, and then I did the Highlands type and the Mare type.
Okay. I guess
And I did
did
not. I'm looking at the. I did not. We did not do agglutinants. We wanted to initially, but it kind of created this like parametric explosion of all the parameters. Professor Yu is really interested in doing a follow-on experiment looking at agglutinates and worms, as there's some other research and literature that worms are capable of digesting volcanic glass. So we might see similar things for certain species of worms.
Yeah, okay. What did you have a were you able to characterize the percentage of organic matter in the regolith after the worm treatment?
Yes, that was that total carbon, total nitrogen, and generally the worms increased or improved the ability for the media to hold on to the carbon.
If you wanted to share your screen again, you could. And
Yeah,
then
so
I guess
that's this data right here, right? So um, uh, even after 1 day, you saw an improved ability to hold on to carbon. And then at 31 days, it not only did it hold the carbon, it actually increased the carbon. So there's a lot of numbers out here, um, but it held the carbon significantly better. And then some of that carbon may have ended up kind of locked up in other kind of organomineral interfaces.
mhm.
The with the highlands doing better at holding carbon, right? So the mare kind of lost carbon as it went along, but it held it better with the worm enhanced, with the worms present, whereas the the highlands dish basically saw no carbon loss over time and held that carbon and locked it up.
Fascinating. We'll do one more question since we're coming up on the coffee break here. Um, what do you think was the least limiting factor in the worms? Was it the structure of the regolith, the nitrogen content?
I guess I'm not quite sure I understand the question.
Yeah, I also don't. Dan, do you want to clarify that? You mean the most limiting factor for regolith transformation? Um, Liebig's law of the minimum? That didn't clarify it for me.
I'm not sure.
Uh, okay,
I'll try
well,
to answer the questions here in the chat, and then people are welcome to reach out to me via email. I'm always happy to chat about it. You can get Adam at oeac.space is one, or I'll throw my university address in the chat here.
perfect. All right, guys. Thanks so much for that, Adam. That was really fascinating. I love to see some good regolith experiments with biology. This is a great example of space ecology. Really appreciate it.
Thank you.
Okay, guys. So we are at our first coffee break, which is 20 minutes, and I guess now it's 18 minutes. So I guess I will meet you all back here in a little bit, okay? Then we'll hear from some more presentations. Thanks, everybody. Hey, Oscar. Glad you could join us.
Yeah, thank you.
Mm.
Good job, man. This is really cool.
I appreciate that. Yeah, I mean, I'm grateful everyone could come here and give these awesome talks. And this is nice because, I get to help choose all of the presentations. So we mostly just listen to things that I'm really interested in. This is my favorite event of the year.
Well, you got good taste.
Yeah, I suspect everyone at this meeting has pretty similar tastes. Um,
Half tempted to ask what that background is.
this is a picture from Biosphere 2 when I was visiting last year.
So you worked there for a while, you
No,
said, or something?
no, I did not get to work there. I did go do a master's at the University of Arizona because it had Biosphere 2, but by the time I got there, they weren't really doing closed ecological
Yeah.
science
So who was
there.
your major professor?
Professor Joel Coelho.
Oh, okay.
Yeah, it was a lot of fun. I did not get to spend as much time in Biosphere 2 as I would have liked, but the door's not closed yet.
Yeah,
Uh,
yeah, sorry, I don't know if we got to go, but I remember they were converting the biosphere and they went to Columbia, and then I guess it went to you guys or something. I don't know. I kind of lost track.
yeah, was it Columbia? Yeah, I think it was. But I think University of Arizona got it in the early 2000s or 2010 or something. But they just do regular ecology and some other stuff there now. Okay, we can talk about it later though, because next up, I'm actually really delighted to introduce the next speaker, Clara, who was an intern at my organization this past year, this spring Institute for Forests on the Moon. And Clara is working on, she's been advancing one of our projects that I had presented on at the International Conference on Environmental Systems and also the Mars Society Convention. But I'll let her explain it, I think. So without further ado, Clara is going to be telling us about The Martian and automating setup of waste treatment systems to minimize astronaut operation time in lunar habitats.
Thanks, Patrick. So hello everyone, I'm Clara Laforêt. I'm currently in my final year of Cognitive Science Engineering School in Bordeaux, France. And today I'm going to present the work I did during my second year internship with the association, the Sprague Institute for Forests on the Moon, which involved automating their waste treatment system on the moon called the Martian. Firstly, what is the Martian? So the Martian addresses an issue. A human produces on average 128 kilograms of fecal waste per year, and each kilogram sent to the lunar surface is estimated to cost about $1.2 million. So if we were to handle this waste the same way it's done on the ISS, so just bagging it and burning it during re-entry, on a 7% moon base, it could cost $1.075 billion per year. So the Martian is designed as an artificial wetland system for waste treatment on the moon, inspired by the French reed bed, a modern alternative to traditional municipal waste treatment plants. The Martian uses gravity to move wastewater from the primary treatment to the secondary treatment zone, and then to a retention basin, where treated water is stored before being reused by the crew. Now we'll see how to automate this system to reduce the operation time of the astronauts. So first of all, I had to identify the human operations in the Martian. So I decided to divide them in 3 phases. The first phase is the setup, which includes preparing the site, creating and installing the container to hold the primary and secondary treatment zone and the retention basin, designing and setting up the condensation and lighting systems, and finally, connecting and testing the whole system to make sure everything is working properly. The second phase is the use of the Martian, which includes producing wastewater, treating it, and then circulating the treated water back into the habitat. The last phase is maintenance. So as you can see in the picture, we were inspired by the maintenance task used for the French red bed treatment wetland on Earth. So we will need to adapt this task to the specific condition of the moon base. But most of the maintenance will consist of small, quick tasks like checkup, while larger tasks such as cleaning will only be needed once or twice a year. Once I identify the human operation, I used the 10-level taxonomy of levels of automation by Mika Slay and David Kaver to determine which parts of the Martian could be automated while still maintaining operator involvement in controlling complex systems and facilitating situational awareness. So I assign each step in each phase to an automation level. To summarize, I notice that the setup phase is very human intensive and could be automated to level 5 or 6, where the system performs action with human support and requires human approval. The use phase will naturally be fully automated once installed, so we can assign it a level 10. And as for maintenance, which only takes a few hours per year, so it could be automated to level 5 with the system performing actions with human support. Next, I focused on deciding which phase to automate between the setup and maintenance phase. So the setup phase is time consuming, but it only occurs once during the initial installation. And in contrast, the maintenance phase takes less time, but happens everywhere. However, fully automating all maintenance tasks is challenging because inspection still require human involvement. Therefore, I decided to focus on automating the setup phase, particularly the creation of materials needed for building the system, such as the primary and secondary treatment zone, the retention basin, and the condensation and lighting systems. First, let's look at the materials needed for building the system. So the primary and secondary treatment zone consist of 2 to 6 millimeters and 6 to 15 millimeters gravel, sand and pipes. And for the condensation and lighting systems, we need several components such as the radiation shield, radiation reflecting coating, filtered sunlight, and others. But what resources could we use to create the Martian? Since each kilogram delivered to the moon can cost up to $500,000, using in situ resources is highly encouraged. So, like the regolith that makes up the moon surface, which ranges from fine dust to rogue glutinate, we will study how to use regolith to create the primary and secondary treatment zones, the retention basin, and the condensation and lighting system. For that, the first step is to collect the regolith and then sort it into different sizes, so 2 to 6 millimeters and 6 to 15 millimeters gravel, and sand for primary and secondary treatments. And then the regolith is transformed or mixed to create plant soils, piles, and structural components. So next, I looked for existing technologies for each point. So for collecting regolith, NASA designed Perseverance by inserting a drill into it using percussion and rotation to take samples of the regolith. But to collect more regolith, NASA also developed the Regolith Advanced Surface Systems Operations Robot, the RACER, which use twin bucket drums that rotate in opposite direction to excavate and collect regolith efficiently. Next, for sorting gravel sizes, I found an innovative method. It's an electrostatic sorting system that leverages electrostatic forces to separate particles based on size. For transforming regolith, NASA funded study showed that research shows from the University of Florida successfully grew Arabidopsis thayana in lunar regolith samples collected during the Apollo missions. However, the plants showed slower growth compared to those grown in Earth soil or lunar soil simulants. Because lunar regolith lacks the nutrients and structure of Earth soil, so researchers are exploring ways to improve it for future agriculture, such as using green compost. To create materials from lunar regolith, researchers mix the regolith with binders to form a homogeneous ink. And then this mixture can be molded or used in 3D printing techniques to build complex structures layer by layer. Finally, I applied these existing technologies to the Martian to determine the materials, time, and energy for each step. So for collecting regolith, I calculated a time of 27 minutes and 36.9 watt per hour to collect 20 kilograms of regolith using the RACER robot. For sorting regolith, according to the Kawamoto study using the electrostatic system, the time is not specified, but the energy required is 0.15 watt per hour to sort 1 kilogram of regolith. Then to transform the regolith into rich soils, we need 0.70 kilograms of regolith and 0.30 kilogram of compost to create 1 kilograms of rich soils. And finally, for mixing the regolith, I decided to calculate the requirements for a pipe that is 1 meter long and 10 centimeters in diameter. I calculated the amount of several binders needed to mix with the regolith, which takes 52 minutes and requires 1,256.64 watt per hour. So to conclude, this presentation highlights the importance of automating systems to reduce the operational time required by astronauts in lunar habitats. But however, it's important that this automation is designed carefully, so human operators can always maintain control over the system. And it shows that the Martian can be effectively automated, allowing astronauts to save significant time during the setup process and focus on other important tasks during their missions. Thank you.
Thank you for that, Clara. That was really interesting. It's great to see a summary of your work. While we're waiting for the questions to come in, I think Jane's question was more for me than for you. I've got a question for you, which was, what part of this setup and construction process were you surprised to find was the most time consuming, and how much time did you save by automating it?
I think maybe the transforming of the regolith with 3D printer, because I think it's very fast, and also I'm surprised to know the sorting regolith machine with electrostatic system. It's very curious to know that.
Okay. I've got another question, but I think it's also more for the concept of the Martian and the automating of it, but maybe you can try to answer. Did you consider to study the use of microorganisms in wastewater treatment?
I think microorganisms play an important role in wastewater treatment for the Martian. I'm not sure to answer this question. Yeah.
That's fair. I mean, the answer is yes. It's
Yeah.
all microbial action. I guess I'll answer maybe some of these other questions in the chat. Jane and Bryce, why a wetland rather than a more compact version? Specifically because the goal of this exercise was to look at ecological systems as solutions, and wastewater treatment wetlands are already in frequent and widespread use here on Earth. It's possible to do the same thing in a box, and in fact, the Spring Institute just got funding to from the French Space Agency to continue working on this, including putting it to a prototype phase. So I suspect we will have more data for you the next time you guys hear about this. Yeah, thanks so much for your presentation, Clara. This is really great. Good to hear from you as well. I think we
Thank
can
you.
go ahead and move on to our next talk, which is Bryce Meyer, and he's going to tell us about key space farm flows for efficiency, algae, plant crops, and fish. Bryce, we can see your screen, though you're still muted.
Let's see.
There you go.
Oh. Yeah, trying to get the camera. There we go. Everybody should be happy now. Sorry about that. Yes, this is vastly simplified for this crowd. I'm going to be honest, because I think this is the first time I presented to this group, though I listened in the past couple years. So this crowd is much more complicated than I usually present to, so I apologize if this is overly simplistic. But the gist is that there's some interesting flows that once you have a complicated enough structure in your space farm, you can figure out that there's some efficiencies that can be gained if you want to have if you've made the decision to have animal protein involved. And even if you don't eat the animal protein, it can be used to produce nutrients for plants, and you can sort of keep them as pets. So if you want to do koi, you can do that too, I guess. So I'm going to talk about my human habitat assumptions, and this one has a lot of numbers that I've sort of worked my way through semi-notionally, right? Data to the farm and other things that are go through, and how the vascular plant, spelling error, crops and mass flows, adding aquatics, so adding the fish, photobioreactors, and getting to balances. So as I said, for this crowd, this is overly simplistic, but the gist is that the purpose of having something like a space farm, whether it's a separate volume or whether it's semi-involved with the habitat itself, is to, of course, process the carbon dioxide, wastewater, and other wastes from the human habitat and return oxygen, water, and food back, right? So the assumption in any space farm idea is that footprint and therefore enclosed volume is a premium, right? Energy may be a premium, maybe not. And then, of course, it needs to be as close cycle as possible because of the mass shipment cost. So this top level farm that I'm going to discuss in here looks something like this, right? I took that same flow, you extend it out, and it will involve aquatic animals, vascular plants, which are typical traditional crops, right? Photobioreactors, and then a waste processing array. Now, this doesn't mean that other processing doesn't happen in other locations. It doesn't mean that there aren't other machinery that happens at each one of the places where you do all this growth. And it doesn't necessarily mean that they're actually physically isolated. Each crop is physically isolated from the others. But the gist is you have a series of standard flows that go through the whole thing, right? And so the big thing to note about mass flow in a space farm scenario is if your menu is complicated enough at all, most of the mass actually cycles inside the farm, and the cycle from human habitat out to the farm is smaller than what's going on inside the farm itself, as long as you have a complicated enough menu. So if you actually have a menu that you actually want to eat for years upon years on end, most of the cycling is happening inside the farm itself. So I went with this kind of dietary assumption. I built this random thing with only four menu items, really? Yeah, 4 menu items, right? Which you could live on, but honestly, you'd have a much more complicated menu in space, and I've done other work that goes to that level. And you can look it all up on my website if you're curious, and I'll put that in the chat at some point. But I had to come up with an initial diet in order to show what the masses are flowing through the whole farm. So this is a 2,000 calorie diet, has some vegetables, a protein crop, rice, and of course tilapia, right? Just a little bit of tilapia every day, just so everybody has a little fillet maybe in the whole choice. The assumption is when you eat tilapia in space, you're going to eat the whole fish. You can't afford just to eat the fillet, right? So that means you have to eat the whole thing. The rest of these crops will deal with the silage and stuff in the next several slides. So we also had to use a human model. This is loosely derived from the NASA model, except it's modified based upon some other assumptions I've seen over the years dealing with human waste outputs and things like that, and knowing that the diet alters how much comes out. So what goes in you as a mass flow comes back out again. So the diet I give you alters what your feces look like, what your urine looks like, and everything else. So these are the assumptions I made, right? So you can see that there's a dry mass output and a water out and waste. These two together combine to make wastewater. And then I assume that there'll be some clean water in that's provided by the overall structure, because you have to flush with something, right? It has to go through you and flush through you to end up out again. But that doesn't mean there aren't other water cycles involved, and I'll show those next. So in reality, if you're living in a human habitat in space, a lot of water cycling is going to happen inside the habitat, right? For one reason, because you don't want mold growing everywhere, and humans produce a lot of water as a result of our aerobic respiration, right? So there will be some water cycling inside the overall structure. You actually release more water in sweat and breath than you pee out, for those who don't know, right? And then you'll have different gray water uses where you do hand washing or washing of things that result in a series of gray water that doesn't contain human waste, but has a minor load of things that are semi-organic, which is going to require us to use organic soaps and things like that. That kind of gray water can actually be pretty quickly processed and sterilized, sent right back around. And I would strongly recommend you have in-habitat plants everywhere you can have them, right? Green walls, along poles, along the walls of hallways and everywhere else. And the reason is it will clean up the smell a lot. And it's a great way to grow, great place to grow spices, right? So the spice plants will clean up the air a bit. And you have plenty of those in the habitat. So if you're going to have a house plant, it might as well be a useful house plant. As a result, you end up with what leaves the habitat, and that's where these numbers come out, right? So as a result, you had about 2 kilograms full of wastewater, and the wastewater has roughly about 0.13 grams of load inside the wastewater, right? And you also have the CO2 coming out, the O2 in, and the food wet mass, right? So the wet mass is what's in that menu that I showed you earlier. We only eat wet mass, we don't eat dry mass, right? And so what happens is in waste processing, this waste tank and bioreactor array, you're going to have a very healthy structure inside of the farm and coming out of the habitat. It could be just a central area just because of the smell and because of the other things that you have to do with this. And you could have a simple array, something like this, where you have a series of tanks that do aerobic digestion of the waste in order to get something that you can send to the farm. So the human waste go through, you sterilize it, and then you let the bacteria work on it a while before you send the nutrient-rich water out to places in the farm. And then the solids, of course, you could either put back into solution or send out to the farm. And then as a result of this process, yes, you're going to produce CO2. Now your question is, I'm using up your O2. Turns out oxygen ain't a problem. So when you grow things in a farm, you actually have excess oxygen, and CO2 becomes something that's precious. And that's because of this, right? So let's say I just have these 3 vascular crops in roughly these quantities, and these represent the mass flow engine that the crop is, right? So for every 1 live kilogram of bell peppers, I can take 5.3 grams of wastewater and some CO2 and come out with some waste wet mass, right? Which is the silage, and then the edible wet mass. So most vascular crops are only about 45% the edible part at best, right? The rest is the inedible part. Right, so if you grow an annual crop like pinto beans, for example, you grow up the pinto beans, you take the beans off, you have this whole rest of the plant and all these roots that you have to do something with, right? And that becomes silage or waste wet mass, right? Same thing for the rice, which becomes the rice straw, roots, leaves, right? Chaff, all the other parts, right? So there's a good chunk of waste wet mass that is generated by each crop, along with the edible wet mass that you chew on. We're talking about how you grow aquatic organisms. So something I mentioned here is this thing called continuous harvest. And so what that means is I'm going to take my plants, and this is already practiced heavily in the pot industry, so this is not something new, right? This is something we already know very well. And what you do is you actually you move plants through a series of growth areas, optimized for that stage in their growth cycle, and you also harvest every day. Right. So as a result, you essentially have a continuous conveyor belt of plants. You start off with seedlings all the way to mature plants that pull out, plant the next seedlings, and rotate back through. Right. There's a whole discussion on exactly how you do this, but that's the gist, and it shrinks the footprint of the overall farm. Same thing can be done with fish or shrimp, right? And you essentially rotate the fish through a series of tanks until you get finally to the harvest tank at the end, right? So tilapia take about 180 days to grow. Here you go, right? And you save some in your breeder tank to produce more tilapia. Now, we don't know exactly how mammals will reproduce in not mammals, but fish will reproduce in 1/6 G or 1/3 G. My bet is they probably can, right? And I would say shrimp even more so, right? So if I swapped out this tilapia with a shrimp, same kind of thing, right? And you're roughly, for every live kilogram of tilapia, you need about 50 cubic meters of tank, right? So that sounds like a lot, but it's actually not. So this is the mass machine of the fish, and you notice I'm feeding it here algae wet mass, and I'm going to get to that. So I could have fed it silage from the rice, right? I could have taken the rice silage, which means all the straw, did some fermentation and fed that to the tilapia too, probably, right? That would work too. Maybe not so much with the pinto beans. You'd have to do some extra fermentation for those in the bell peppers to get out some of the other side chemical compounds. But the rice you could definitely do it with, right? It's a possibility. But I would have to plant extra rice. So let's say I used algae in this case. And I got the algae from a photobioreactor. So photobioreactors are extremely small, compressed types of structures that can generate a lot of algal cells very quickly, right? And so it's essentially exposing the algae cells using oxygenation, in this case, carbonation, right, to the solution, and then extracting the oxygen that's produced using light, right? So light is the processor. And again, wastewater comes in. The algae eats the wastewater. It can't have a high solid load. It's got to be mostly fully solution, right? It can't be something that has a lot of solids because they'll just collect on the bottom and gob up the whole works. But as long as you've already done some settling with the waste and pulled off the nice juicy stuff at the top, you're better off, right? You can do that. And then it's not as simple as just pulling out the oxygen. Obviously, you probably are going to have some kind of a gas separator here, maybe a cold trap or something similar, in order to pull out the oxygen and then recycle the CO2 back through the process. And at the bottom, of course, you settle out the algal mass. You might need a centrifuge on the moon, right? Because it might take too long for those algal masses to settle on the bottom otherwise. But this is the basic mass machine for the photobioreactor, something like this. As a result, you can get up with this huge mass flow that looks like this, right? So in this particular case, you can follow all the bouncing datagrams around. And if you notice, the stuff coming in and out of the humans is smaller than this whole pile of things away from the humans through the farm, right? Even in this very simple scenario. And it becomes much more prevalent if you add something that's actually going to look like a long-term diet where you're not just having 3 vascular crops and a tilapia, right? If you have something that has 15, 20, 30 types of crops in here, and you have hundreds of people, then this mass flow in the farm is several orders larger than just human to farm and back. Right. You also notice that there's a large wastewater treatment part, and that's why I showed you that array earlier. So something that you have to deal with. So let's just say I'm going through here. If you notice, I've got all these pretty numbers all wonderfully balanced out. It ain't quite that simple. Turns out that overall in the farm, you have plenty of oxygen as you go through the crops. You never have enough carbon dioxide, even with a photobioreactor. Never have enough, right? Humans just don't exhale enough to feed themselves. They don't. right? Some of that is due to the silage problem, right? That's one of the biggest reasons is the silage itself, is so that even if you tried to do this with any of those vascular plants, unless you're eating something like lettuce and you magically figure out a way to fully digest it, not going to happen, right? You have to somehow crack the CO2 back out of all that silage and the water that's in it too, right? So it turns out I can take my wastes and add them to the equation. I can do the tilapia, and this is a very simplistic structure compared to the flow you just saw, right? But if you get the simple math here, you can see that I've got wastes, right? I've got plenty of dry mass waste down here. And then I need water, right? I need clean water that can go back to the habitat, right? And so the way I get that is two ways. One is I dehydrate the silage. So I take that rice straw, that leftovers from the bean plant and everything else, and I dehydrate it first. And that shouldn't be too hard given the fact I got vacuum all around me, right? So I dehydrate all that. I get out that clean water right away. That leaves me more the dry mass component that's left in there. I take that, and now I've got some options. I could try to use another series of aerobic bioreactor arrays, which take a long time, and at this point would take a lot of space to crack that last little bit, especially as Jane would point out, the lignin, right? So as a result, you're probably going to start off with a tank, and it's going to go to an incinerator, right? So the beauty of an incinerator in this case is I'm going to burn until there's nothing left, right? There would be ash. It's not zero, but it's something small, right? You're going to have some small percentage of ash. I don't like to use incinerators if I can avoid it because the ash is not as bioavailable to my crops, right? It's not as available as if I used a normal natural process to digest it. But as a result, this combustor now takes the excess oxygen and results in the CO2 balance and the remaining clean water that I need. So really, this is the big flow that I'm trying to illustrate in this overall prezo, right? This photobioreactor to animals to plants. So I've done it before where I've taken out the photobioreactor, right? And just had the aquatic plants eat the silage, and that takes a lot more room, right? The photobioreactor is 18 times more efficient in size. And as a result, more efficient in energy and everything else than adding more vascular plants would be. So the next thing people ask is why not just dump the tilapia and grow more beans, right? If I do that, now I have to have a much larger processor for this previous structure, for here and this previous array here, than I had to have before. And I also grow a far larger number of vascular plants to counteract the fact that I'm missing all those extra nutrients that are in those tilapia. Right. So when I've done this in the past, it's added a good 15% to the footprint of the farm by getting rid of the fish. So theoretically, even if you don't eat the fish, even if you just grow them for fun, their role in nutrient processing shrinks the overall size of the farm as long as you feed them algae. Right. So that's sort of a tack here. You could replace them with koi if you want, and just have a big park where everybody walks through and you have a little stream with a bunch of koi in it. That would sort of work too, right? Bunch of actually without koi would be better replaced by Asian carp, different discussion, right? But having these animals in here and feeding them algae just knocks off that extra 15% of enclosed volume, right? Which is huge, right? So something to think about is the fact that we've always created our space farms and we never talk about including animals anywhere in the equation. If you're going to have a fully mature farm, you're going to need something that supplements this result, right? It doesn't mean that they have to be aquatic animals. I've always championed them because they're very efficient overall in nature. But I mean, you could use crickets, you could use other things like the tenebro larvae, aka mealworms, right? You could use other different animals that fill the same role. Or you could create a large-scale bioreactor that uses yeast and bacteria to do the same thing as well, right? I'm not saying you have to have them, but why not have something like this and add a little dietary variety? That's just my 2 cents. So overall, if you have fish or shrimp in the whole equation, just make damn sure they can eat algae. So that means no rainbow trout. That means no catfish. That doesn't means no salmon. right? You have to select species that really, it's really optimal if they can eat algae, right? And there's a lot of, nature has provided us with a lot of fish that grow real fast on that, and same with shrimp, right? Photobioreactors are really good at producing dry mass and oxygen for the size and time that you have available, right? They're just really good at closing the loop. If nothing else, they could just be like a capacitor for your overall space farm mass flow, right? Just like any bioreactor you have for aerobic digestion or anything like that, the photobioreactor adds a capacitance effect in the overall mass flow of the farm and allows me to buffer out oopses, right? Buffer out things that might happen in the process of running things through this overall large scale food factory for all intents and purposes. A factory that's going to have to be monitored by AI, use SCADA technologies, and a lot of other mechanisms that are available. So combining fish and photoreactors adds a nice protein source that is honestly yummy. You have to eat the whole fish, right? Same with the shrimp. You have to eat the whole shrimp, right? But it's a very small area to grow those fish or shrimp, and it can provide bioavailable nutrients to the crops and honestly to you, right? We already talked about B12. There you go. So that's all I got.
Thanks for that, Bryce. That was really interesting. And I think despite your disclaimers at the beginning, it was not too simple for this group. I did like the takeaway that perhaps animals can actually reduce the overall footprint. I am afraid we don't have time for questions,
Oh,
unfortunately.
sorry.
No, it's okay. Maybe if people want to put them in the chat, you can find them and answer them. Or you can still answer things directly in the Q&A. But next up is Marshall Porterfield, who is supposed to tell us about the biophysics and mass transport in ecosystems engineering. Marshall, are you around to present? I actually don't see Marshall in the list, which is weird because he was here earlier. Well, I guess rather than waiting an indeterminate amount of time, hey, Mara, are you still around?
Yes, I'm still around.
I think it's your time to shine.
Sounds good. I have my presentation ready.
All right. Thanks for being available on standby.
No
I think
worries.
you're gonna have to present your own title because I don't have it on me, unfortunately.
Sounds good. Let me just go back to the presentation. Okay. Alrighty. Okay. Check. Okay. Am I now sharing my presentation? Not yet.
Not yet.
Okay. And just all right. Options. I don't. Am I allowed to share
Yeah.
my?
Do you see the big green share button in the bottom
Oh
of the
yes, yeah. I was
right?
looking like at the little dots. So yeah, great. All right. Can you see what I'm seeing now?
We're still just seeing you.
Okay. Let me just check. I don't know what's going on. Okay, there you go. I think yes. All right. So desktop. Okay.
Mara, okay, there we go. Yeah, now we can see it.
All right. Good. Let's just check. Yes. All right. Good.
Yep.
Okay. So my presentation is in regards to the sustainable plastic production for deep space 3D printing. It was part of my PhD work, which is now finished. I did my PhD at the University of Westminster in London. And now I'm working at the Open University. Now I'm trying to find, so my background is microbiology. What I love about microbiology is the fact that all the products that microbes can give to us. So right now I'm trying to find new novel antibiotics from extreme environments, in particular from salt environments. But in terms of my PhD, and what I'm going to talk about was extraction of bioplastics from microbes, so we can use them for 3D printing in space. And so in terms of my thesis dissertation, which is now concluded, if you are interested, on the left I have, it's called Implications of Microorganisms in Future Crew Missions to Mars. So my PhD was very focused on future missions to Mars. And as a microbiologist, in regards to the applications, I look at photosynthetic microbes and the kind of products, and particularly bioplastics, what can they give to us? But I also have another component, which I'm not going to talk here. Instead of microbiology, like future astronauts will go to Mars, and they will, we'll sterilize everything except ourselves. So we'll take with us microbial human associated microbes, and also analyze the risk of human associated microbes contaminated the Martian surface and interfering with the search for life. So in regards to the use of photosynthetic microbes for sustaining human life on Mars on deep space missions, this is this is an image that me and my colleagues did for a review paper that we did. If you are interested, I have the reference at the end about the very various applications that microbiology have for Mars. Here, this is how we imagine in our heads in terms of in situ resource utilization. We can get CO2. So microbiology, we need CO2 to grow, so we'll get it from the atmosphere. We can mine the regolith for some minerals, and then we can have different bioreactors. Microbiology can give us a lot of products. One of those bioreactors could be responsible for producing bioplastics that we will need for 3D printing. Here's another image of our review paper, if you're interested. And this is a period of the most important products that we'll have that we'll need on space, and that microbiology can give to us, starting obviously by oxygen, food, and water. We've heard a lot today, and so I'm going to talk about biopolymers. And a lot of you know why microalgae are great green factories. They're fast growing, easy to cultivate, photosynthetic, so they will need is sunlight and carbon dioxide that exists on the Martian surface. And they have simple grow requirements: water, sunlight, a few nutrients. They have a small land footprint, and they can adapt. Different species can adapt to various environments, including extreme environments. I will particularly talk ahead of my microbiology of choice. So that was Chlamydomonas, which I used to produce the bioplastic, and I will explain a little bit further ahead why. So 3D printing in space has been done. This is aboard the International Space Station. This is Commander Barry Wilmore, that on the left is holding the first object ever 3D printed on space. On the right, the first 3D printed object with functionality was a bridge. This was done in collaboration with Made in Space. But these are produced with ABS filament, which is not biodegradable. There's a lot of in 3D printing. One of the most plastics most known, it's PLA, which is biodegradable, but it's biodegradable under industrial conditions and there are very high elevated temperatures. So what I want to has we all talking about, we need closed loops, we need a plastics that are biodegradable. And so I looked at a family of plastics called polyhydroxylamates. You can just call them, as I do, like PHAs. And so PHAs, there are various types of PHAs, and they are a repetitive polymer chain of hydroalkanoate monomers. You can have PHAs are short-lived, short chain, and that will increase the stiffness and it will be more stiff, and the longer ones will be more flexible. And the great thing about PHB is that it is biodegradable in the soil, in water, under aerobic and aerobic conditions. And so that's why I looked at them. They're not also biodegradable. They also biocompatible. They are very used in medicine. They're starting to be used in medicine, and they also, depending on the type, they're also easy to process, and they can be processed with the type of the same equipment of the types of industrial equipment that we already have to process conventional other types of plastics. Within the family of PHAs, sorry, I'm just trying to, slide is not moving for some reason. Okay, there you go. Within the family of PHAs, we have PHB, polyhydroxyborate, which is my bioplastic of choice. The PHB, it is the most well characterized bioplastic. It is strong because it's short-lived. It is commonly used, it's starting to be very used in packaging and also medical applications. And PHB is produced by various bacteria, including cyanobacteria. The disadvantages of PHB is right now the cost is expensive, and it's expensive because all these bacteria need a carbon source to grow. So PHB is produced within the bacteria under certain nutrient conditions. And it's usually one of the best approaches is when the nutrient conditions have limited nitrogen and excessive carbon. So you need a lot of organic carbon. The problem, organic carbon, it could be expensive. There's no organic carbon, for example, on Mars, a place that my PhD was focused on. And the problem with, in terms of like microalgae, there've been a lot of attempts to genetic engineer, but there's also some cyanobacteria that can produce PHB, but they produce PHB at lower yields than other bacteria like the genus Bacillus. So what I thought was like, there's a lot of possibilities. I could genetically engineer. I could try to find other cyanobacteria that could produce PHB, but what I tried to do was to create a system that could couple Bacillus with a microalgae. So the microalgae could give, as I said before, microalgae can give us food, oxygen, a lot of products, but it can also be a source of organic carbon. Why? Because some of them, like Chlamydomonas, my microalgae choice, produce a significant amount of starch, and starch can be hydrolyzed and be used as an organic source for other ectotrophic microorganisms such as Bacillus. So as I say, I chose Chlamydomonas because it's a model organism. It is also well characterized. It's easy and quick to cultivate. It has genetic tools if I wanted to genetic manipulate. But then again, one of the main things was the fact that he has a high quantity of starch. So basically, I just want to couple these two so I can get bioplastics, or I can get PHB out of that. And here I just wanted to show you how on the first figure on the left, Bacillus is accumulating PHB as a carbon storage, as I say, under nutrient limited conditions. When it's stressed, when it lacks nitrogen and it's stressed, is going to produce this little walls, as you can see, inside itself, so it can storage the carbon and use it later, so we won't starve. On the right, you have Chlamydia that also under nitrogen limited conditions can also produce starch, and you can also see around here during photosynthesis. So, oops, sorry. So my goal was to produce this biphasic system from scratch, because my university, we don't work with, we don't do this kind of work with microalgae. But I wanted in the first stage to grow a lot of Chlamydomonas. Then I want to harvest that biomass and then hydrolyze the starch. And with the starch, I will break up the starch, and it will give me glucose that I can use to feed bacillus. And the bacillus, instead of using the commercial glucose, which can be expensive and it's not available on places like Mars, I can use now the glucose that I got from the starch that will fill the bacillus, and then I'll produce the bacillus and I extract the biopolymer, and then I try to produce two D films and also 3D structures. But as I said before, there was no like big bioreactor in my university, so I had to build that from scratch. I had a place like Mars in mind. So in terms of large scale, I built a bioreactor that would fit 120 liters. It was there's a lot of types of bioreactors. I chose one called hanging bags because it's one of the simplest. When a place like Mars, I thought about how can I make a very easy bioreactor that could be taken to Mars with very simple components. So I was able to do that. Here you can see on the left my bioreactor, which could support 6 hanging bags, and these bags had three in the front and 3 in the back. Each one could use to cultivate with around 15 to 20 liters. And so for microalgae growth, you would need lighting system. As you can see behind the bags, there's two panels that will provide the proper lighting. Then I had a big support that I made from scratch. Also, if you see those little tubes coming at the very bottom of the bags, they provide air. So I selected aquarium air pumps, really basic. So everything was just really basic. And the air coming out will provide a gas exchange, but also will mix the cultures, will mix the media properly. And so I was able to set that up. I got my biomass. This is at the very beginning. Then they become very green. I extracted the biomass, the liquid. I separated with centrifugation, and then I hydrolyzed the mass. I tested different techniques. What was the best hydrolyzing techniques? I chose acid, which is something that I try to improve later. But I chose acid, and I was able to degrade the starch to glucose. Then I fed into the bacillus bacteria, as I said before. And then when I got my bioplastic, I produce 2D films like this one over here. And then I produce 3D medical scaffolds. And I produced this with the starch obtained from microalgae, but I also compare that with the conventional glucose. What if the bacillus are grown with a conventional glucose? And what I noticed was that the 2D films actually had increased flexibility. As I said before, PHP is a short chain polymer, therefore very stiff. So the good thing about it is it was with glucose from the microalgae, I actually was able to increase the flexibility, which has great applications again for packaging and things that require a lot of flexibility, and also produce a 3D medical scaffold who had interconnected poros, but it was susceptible to fracture. So in terms of comparison with the glucose from microalgae and the glucose from commercial glucose, is that I increased the flexibility, which obviously has advantages in terms of packaging and whenever you require some flexibility. But of course, it has disadvantages when you want to 3D print and to make to make more stiff structures, like for example 3D printing. So in addition to that, oops, sorry. In addition to that, I also want to test PHB and the copolymer PHBV in terms of 3D printing. So I looked for some available blends, and I found two blends. That one was PLA with PHBV, and the other one was PLA with PHB. And what I noticed was, and so what I wanted to replicate, you see again, the commander with a wretch. I wanted to replicate this because again, it was the first wretch that was utilized in space. And for the one with the PHB that you can see on the second image, B below, you can see, no, sorry, it's the PLA with PHB is actually the first one. You can see that due to the stiffness, due to the stiffness of PHB, the first wedge on the top is kind of bended, and also it didn't work properly because I actually have it here, and you can actually turn this around. It comes off exactly like the one from the commander. And this is actually, I used the same file. So Made in Space sent the file, sent the order. They sent a printer to the ISS. And so the order was sent from Earth, and then it was printed on space, and it was functional. And so with PHB, because of its stiffness, it was bended, as I show, it was not functional. But actually with the copolymer PHBV, is actually, you can actually see that it rotates and everything. So, which was exciting to find out. So in terms of major conclusions, oops, sorry. The copolymer was easier to print, were less prone to rub, and the only one to properly work in comparison to PHB, meaning that PHB still has some work to do in terms of being properly used for 3D printing applications, yet using glucose from microalgae actually gave me a PHB that was actually less brittle, less stiff than the one obtained with glucose, which is hopeful. And more research on this can actually in the future lead to the use of PHB for proper 3D printing applications, but still promising results, even not for the 3D printing yet, but at least for producing 3D films or 3D structures that would just require mold, but not 3D printing itself. So to produce whatever astronauts might need on site. I would like to thank my my team. Me and my colleague Marina, shown here on the left. We were the first students in astrobiology in space in our university, which brought a lot of challenges, but it was great. I want to thank to my supervisor Louis Dardanel. And here, if you want to know more, we also collaborated with UCL in London. Dr. Saul Porton Lab does a lot of great work with microalgae. And also my other work was with Dr. Michael Macy, which is now working and doing that antibiotic research. So this is the reference if you want to know more about microalgae applications, and that I already gave the name of my thesis if you want to know more about this work and more about the details. Yeah, so thank you so much.
Thank you, Mara. That was really cool. It's great to see the applications of this biological manufacturing. I think people often hand wave like, oh yeah, you can just create bioplastics, but to see someone actually go through the whole process of growing the plastic as algae and then like manufacturing something useful, really fantastic to see the whole thing. We are a little bit over time, which is okay because you started late and we're just running up against lunch, so no biggie, but rather than doing questions, I think I'm going to ask people to put the questions in the Q&A or in the chat, and I'd ask you to answer them via text, if that's okay. Yeah, thanks again for stepping in. Yeah, this is great, Mara. So to stay on track, we have our last presentation before lunch, and it's going to be Luke, who's telling us about a simulated high CO2 spaceflight environment, increasing the plant preference for ammonium as a nitrogen source. Luke.
Thanks, Patrick. Can you hear me fine?
Yep.
Great. Let me share my screen. Okay, you see that?
Mm-hmm.
Great. So yeah, thanks for having me back, Patrick. I'm going to be presenting a similar thing. So if you were here last year, it's kind of I guess a year further on from where I was last year. I've done a lot of work with nitrogen cycling in the past. My PhD was on soil nitrogen cycling, and kind of switched tack during my PhD to look at plant nitrogen uptake, and specifically which different forms of nitrogen they take up. So I'll cover some of the work that I've been doing over the last year in that context, particularly in response to high CO2. So I'm not going to talk about why we grow plants in space or anything like that, because it's already been covered pretty well by everybody else, and I guess I'd be preaching to the choir here. So I did want to just touch briefly on elevated CO2 and the problem that we are facing with elevated CO2 at the moment, and as is currently projected going into the future. So CO2 on Earth at the moment, depending where you get your estimates from, is around 420 parts per million. And that's up a lot. It's increased a lot in the last 100 years, of course, predominantly due to human activities. And that's projected to continue increasing. And that, again, that increase changes depending on where you get your estimate from, what measures we put in place to try and mitigate that. But we're looking in the region of 6 to 1100 ppm by the end of this century, which is, I hope I'm not the only one thinking that's absolutely terrifying. And so just to put into context, when we think about the spaceflight environment, that is much, much higher. So often in the region of 3,000 parts per million currently on the International Space Station. And that is because we have this fully closed environment, of course, because we're in a vacuum of space. And we have astronauts breathing out. The crews are actually increasing in size as well. Often have 10, 11 crew members on board the ISS at the moment. And even though we do have chemical scrubbing technologies to remove CO2 from the cabin atmosphere, which are improving all of the time, we still have a lot of residual CO2 left over. And 3,000 ppm is kind of where it hovers around at the moment. So the question, of course, is if we're going to grow plants in this spaceflight environment, how are they going to respond to this, what we call super elevated CO2? So that is a question that I've been trying to answer. And as I say, I've been looking at nitrogen uptake as one of the major physiological factors that is affected by this high CO2. So, of course, again, we all know nitrogen is a crucial nutrient for plant survival, one of the most important nutrients after carbon, of course. And in agriculture, horticulture, we tend to use inorganic forms of nitrogen. So ammonium and nitrate are the dominant forms of nitrogen that are given to crops. So plants can take up both of these forms of nitrogen, but they can show a preference for either ammonium or nitrate. And that's dependent on several different factors. The most important one being the environment. Of course, that's a large category. There's a lot of things within that can affect this nitrogen preference. Plant physiology also plays a role. So, ammonium becomes toxic to plants in relatively low concentrations, whereas nitrate does not. However, on the flip side of that, there is a much higher associated energy cost with utilizing nitrate as a nitrogen source compared to ammonium. So I think the estimate is around 45% more energy has to be used to reduce nitrate to ammonium before it can be assimilated into amino acids. We also have the growth substrate. I'm not going to touch on that today, but ammonium and nitrate have different charges, right? So they interact differently with soil, with ammonium absorbed into clay particles in soil and nitrate not. So because it's negatively charged, it's much more mobile in soil, that has a lot of impacts as well. But either, that extends into other growth substrates as well. So of course, the key factor I'm going to focus on today is the influence of elevated CO2 on this nitrogen uptake and preference. So it really started when I came across this study 5 or 6 years ago when I was just starting my PhD. This is a study from Arnold Bloom and his group over at UC Davis, and they've been working in this field for, I don't know, at least 20 years now. And this is just kind of one subset of one figure in one of their papers. And here what we can see is, so they're interested in how these plants are responding to future climate scenarios, particularly elevated CO2. So I just want to note here, because it's not actually written on here, the ambient CO2 here is 410 ppm, so very close to that estimate I showed at the start. And the elevated CO2 is 720 ppm, which at the time was what the prediction was by the year 2050 or 2100, I forget. But those are the kind of CO2 concentrations they're using here. And really the take-home message from this slide is that we can see that if you look on the left-hand side here, so this is showing relative growth rate of loblolly pine seedlings. This is several different crop species. You can see that at elevated CO2, when only nitrate is given to the plant, so this left chart here, then the relative growth rate is actually significantly reduced to elevated CO2 compared to ambient CO2. But that's not the case when ammonium is provided as a sole nitrogen source. The relative growth rate is unaffected, perhaps even slightly enhanced at some CO2 concentrations. So this was kind of unusual. Most people, or most researchers, tend to think that nitrate is the dominant nitrogen source in most systems, and therefore plants grow better on nitrate. But here it seems that elevated CO2, that is not true. So what's going on here? Well, I'm not going to talk too much about this for the sake of time, but I'm happy to discuss it afterwards into the lunch break if people are interested. But really the take-home message here is that it's all about the amount of reductant that is available, specifically for nitrate reduction. So I said that plants can take up both nitrate and ammonium as a nitrogen source. If they take up ammonium, that's already in its reduced form, that can be directly assimilated into amino acids. If nitrate is taken up, it must first be converted or reduced to ammonium before it can be assimilated. That requires a lot of energy, and that requires a reductant in the form of NADH and NADPH. Now, that can come from two sources in general. So it can come from photosynthesis, the light-dependent reactions of photosynthesis, and it can also come from photorespiration. So ambient CO2, now, of course, the NADH and NADPH is also used for carbon fixation in the light-independent reactions of photosynthesis. But if carbon is limiting, then there is actually surplus reductant that is available that the plant diverts to nitrate reduction. At elevated CO2, however, you have a greater need for reductant for carbon fixation, and therefore there is less, sometimes even very little, surplus reductant available for nitrate reduction. At the same time, you have this elevated CO2 is actually inhibiting the process of photorespiration, which is also limiting that supply of reductant. Both of those mean that if you grow a plant only on nitrate at elevated CO2, they can no longer do this nitrate reduction process as efficiently in their leaves, and therefore their relative growth rate is affected because they're not assimilating this nitrogen into amino acids. Whereas if they're given ammonium directly, they bypass this process and are therefore relatively unaffected. So that's kind of a brief snapshot of what's going on. So the question that I have is really, does this happen across different species, particularly candidate space crops? Does this happen at ISS level CO2, right? Because I mentioned before that 720 ppm and 3000 ppm are very different CO2 conditions. So do we still see this? Is it worse at this ISS level CO2? And really what happens if you give them both forms of nitrogen at the same time? So all of these studies have been giving the plants either only ammonium or only nitrate and forcing them to use that nitrogen source. So what happens if we give the plant a choice? Do they still choose to take up more ammonium at elevated CO2? So that was really the question that I'm trying to answer. So to do that, I use what we call a differential labeling approach. So this is using the stable isotope 15N. So we have an NFT hydroponic system that we built from scratch at Kennedy Space Center. And I'll show a photo of that in the next slide. And it's a two-tiered system, but each tier is completely independent of the other one. So each tier has its own nutrient reservoir, but we grow the same plants in both of these tiers. There are actually LED lights on both tiers. I've just omitted those from the bottom tier for illustrative purposes. But and we grow the plants in a complete nutrient solution that we make from scratch, but we provide nitrogen solely as ammonium nitrate. So we're giving the plants that choice of 50% ammonium, 50% nitrate. And I should mention at this point that we're growing lettuce. So lettuce is a candidate space crop, as you all know. We're growing 4 different varieties, which I'll cover on the next slide. Some have been grown in space, and we have one that is an heirloom variety as kind of a comparison. And we grow these lettuce plants for 21 days in this NFT system, either at ambient CO2 of 410 ppm or elevated CO2, ISS level CO2 of 3000 ppm. And we monitor ammonium and nitrate concentrations along with pH and EC, and we adjust or replenish, I should say, the nutrient solution to maintain those ammonium and nitrate concentrations. At the 21-day mark, the lettuce plants are in their exponential growth phase now. They're starting to take up a lot of nitrogen from the system. And at this point, we replace the nitrogen in one of the nutrient reservoirs with ammonium nitrate, but the ammonium N is 15N labeled. And in the other system, we do the same thing, except it's the nitrate N that is 15N labeled. So that's where the differential labeling comes into play. We grow those for a further 24 hours before harvesting. We do all the usual harvest metrics, of course, which I'm not going to talk about today for the sake of time, but we collect and dry the shoot material. We then grind it into a powder, send it for isotope ratio mass spectrometry analysis, and that gives us a value of the 15N content of those plants. So it can't tell whether the 15N came from ammonium or nitrate, but that's okay because we know that all the plants on the top tier, for example, saw the ammonium label, all the plants on the bottom tier saw the nitrate label. So it gives you an idea of how much of the 2 different nitrogen forms these plants are taking up in these conditions. So that raw data can actually tell us quite a bit, and I'll show you in a couple of slides a little bit of that data. But we can actually calculate a nitrogen preference value from this data. And it's a very simple value to calculate. All we do is we take the ammonium 15N signal for a given variety under a given CO2 concentration, and we subtract it from the same, but the nitrate label values. So if the value is negative, that means the ammonium 15N signal is larger, so they are ammonium preferring. If you have a positive value, then the opposite is true, they're nitrate preferring. So this is just what the system looks like very quickly with lettuce plants growing in it. We have 2 of these in 2 separate growth chambers, and we're using black-seeded Simpson, which is our heirloom variety, and then we have 3 spaceflight grown varieties of lettuce, Dragoon, Outrageous, and Walnuts dark green. So if we look at the raw data, the 15N atom percent signatures that come back from the isotope ratio mass spec analysis, we can already start to get a little bit of a picture about what's going on here with the uptake of the 2 different nitrogen forms. So here, this is a little bit of an eye chart. So the take-home message really here is that in every graph in this chart, we can see that the value on the left, the yellow bars, which are the ammonium signal, are significantly larger than the bars on the right, which is the nitrate signal. And that's irrespective of lettuce variety, irrespective of CO2 concentration. So it's really showing that the plants are significantly ammonium preferring, irrespective of those conditions, in all conditions in this hydroponic cultivation. And that's not entirely surprising and has been seen in previous studies because it comes back to this physiological effect. So we can see if you have, so if usually environment plays a large role, right, in determining the relative availability of ammonium nitrate, and that can drive preference. But in a hydroponic system, you remove all of those environmental constraints, with the exception of CO2 in this case. So the plant resorts to the physiological drivers. The main one, which is energy expenditure. Ammonium costs a lot less to use for the plant, so they tend to take up a lot more nitrogen as ammonium. So even though, despite the fact that all of these plants are ammonium preferring under all of these conditions, the varieties themselves do actually show significant variation in their nitrogen preference. So this is now looking at those N preference values that I talked about in the previous slide. So we can see that even though they are all negative values, so they're all ammonium preferring, they are ammonia preferring to different extents. And we're still trying to tease apart why this might be the case. So we're fairly confident that this trend is real. But we're starting to think that perhaps it's to do with the plant size or their nitrogen content, the nitrogen demand that these plants have. So we're still trying to delve into that a little bit further. So hopefully there's going to be more to come on that in the next few months. But this is really the I guess the main point of this talk and the main result from this experiment. So here we're showing again the 4 different lettuce varieties and their nitrogen preference values at ambient CO2 on the left and elevated CO2 on the right. And we can see that in all 4 cases, the preference value at elevated CO2 is more negative than the value at ambient CO2, suggesting that the plants are more ammonium preferring under elevated CO2 conditions, even under an already significantly ammonium preferring background. So this high CO2 is actually forcing the plants to take up more nitrogen as ammonium, even when nitrate is still available to them, which is the result that we expected, but it's of course always nice to see data that actually backs that up. So I'll just note here that's only significant for outrageous and Mormon's dark green, but the trend is the same for all 4 lettuce varieties. So I will stop there and conclude. So obviously we're seeing that lettuce plants prefer ammonium as a nitrogen source under hydroponic cultivation, but this is exacerbated by ISS level elevated CO2. So we would argue that future nutrient formulations for space crop production should favor ammonium as a dominant nitrogen source, if this holds true for other candidate space crops as well. But at the very least, I'm a proponent of the idea that we should not consider nitrogen as an element that plants, a nutrient that plants need. We should consider them as ammonium and nitrate and consider them separately, because they don't always behave the same way, depending on which form is available to the plants. And of course, this has a lot of, I guess it's a hot topic as we've seen over the last couple of days. This has a lot of implications for waste processing, nutrient recycling as well. Because if this is true, then we perhaps want more of our recycled nitrogen to be in the form of ammonium, as opposed to nitrate if we are growing in this space environment. So of course, when we're recycling urine, predominantly that is in the form of urea and ammonium. And at the moment, we are then adding this urine waste to a bioreactor full of nitrifiers to nitrify back to nitrate, when actually we might not need to do that step, or may need to do it to less of an extent to supplement the ammonium to prevent that toxicity. So that's one thing we're looking at now, is what is the optimal ratio for ammonium to nitrate? Can we push the ammonium to be higher? And again, is that just at elevated CO2? So those are some of the things that we're thinking about at the moment. So I'd like to thank all of my advisors, everybody that's helped me in this project, Joya, Ellison and Ray at Kennedy Space Center. My 2 interns, Chris and Annie, have been fantastic. The rest of the KSC team for their immeasurable help in these experiments are quite big, and we've run them several times now, so always appreciate the help with those harvests. And I'd like to thank the NASA postdoctoral program for funding this research. So with that, I'll end and I'll take questions if there's time, and if not, I'll answer them in the chat. Thanks.
Thank you, Luke. That was pretty incredible. It feels like there are some really big implications in there, like that will impact how we do agriculture in the coming century. As CO2 levels continue to rise, we'll have to reformulate our fertilizers and consider how we're applying them. I did like how you pointed out that ammonia is already in the reduced form, and so it doesn't make sense. Going back to what people were saying, composting in space is going to be pretty critical. Instead of trying to get the nitrifiers back in the loop, we should just apply it directly. Yeah, that's really interesting stuff. I think we've got some questions. Oscar asked, what were the yields of less and more NH4 preferring lettuce in eCO2?
So I'm still going through that data at the moment, but really there were not. My first thought was that perhaps the the black-seeded Simpson, for example, they're the biggest plants, and they're also the most ammonium preferring. So perhaps there's some link there, but there's actually very little difference in the biomass between elevated CO2 and ambient CO2. But I think that is partially because of the way we run the experiment. So we only ran for 21 days. So this is a toss-up because it's kind of annoying because I have to maintain the ammonium and nitrate concentrations. And even though I use relatively low concentrations because I'm replacing so often, you get to the exponential growth phase and you're having to replace this nutrient solution every day. It becomes very wasteful. So we kind of shortened the growth period. So if you'd left them for a full 28-day harvest, I think you would start to see more of those differences in biomass as you have another full week of this exponential growth. So that is something that I'm going to be implemented in the fall is growing for a 28-day harvest, focusing more on these harvest metrics and that kind of thing, less on the stable isotopes, to really see what is actually going on physiologically with the plants. How do they respond? How does that influence productivity when we give them different ratios of these ammonium and nitrate?
Marshall asks, what about the redox requirements for nitrate reduction and rhizosphere pH affecting the other nutrient fluxes?
That's a very good point. Yeah. So pH is this thing that we always keep coming back to, right? So I made the comment yesterday after Frida's talk. You're always going to have these issues, right? Because classically, when we've given the plants only nitrate, the pH goes up, right? So you then have to add a lot of acid to control that. Here, of course, we're going to have the opposite effect, where the ammonium uptake actually acidifies. In this case, the nutrient solution, it would be the rhizosphere in soil. So it goes the other way, and it comes back to this: is there some balance of supplying ammonium and nitrate where we can balance these fluxes in pH? But absolutely right. I mean, one of the symptoms of ammonium toxicity is that it affects the uptake of other cations if there is too much ammonium in the system. So absolutely, it will affect uptake of other cations. So really the question is what balance do we need to strike to control for all of these things, and that's something that we're hoping to look at going into the future.
Yeah.
There's one other follow-up. There's also a metabolic cost associated with nitrate and ammonia, and I actually have some really good data I can share with you later on that.
Yeah, that would be great, Marshall. Thanks.
Sweet. Well, I think I want to call it here for lunch so people can feel free to be released. But there are a couple of questions in the Q&A thing if you want to stick around for a minute to answer those, Luke.
Yeah, sure. I'll do that now.
I appreciate that. So just for everyone's reference, we're on the lunch break. This is the halfway point of day 2. Like yesterday, it's scheduled to be from 11:20 to 12:30 Pacific Daylight Time. We're already about 7 minutes into it, but that's fine. So I guess I will see you all back here in an hour. I will pop in periodically to check if anyone needs help with something or technical stuff. But yeah, expect to hear from Davi Souza when we all come back. Thanks, guys.
Hey, Patrick.
Hey, Davi, how are you?
Great. What about you, man?
Doing pretty good. Yeah, I just got back from a wedding in Portugal, which was really lovely.
Okay. Are you going to, by chance, to IAC?
Nah, I just got back from Europe. I'm not going there again.
Okay, got it, got it.
Are you planning to go to IAC?
I wish, man. I have exams.
Oh yeah, I see.
Yeah,
Yeah, I still have never been to IAC, which is it's a bummer, but it's always at a bad time for me.
yeah, yeah. That same here, same for me. Hopefully, at least every year we have a new opportunity to try to go.
Yeah. Next year I'm planning to go to the Melissa conference. Are you familiar with that?
Yeah, yeah,
Okay,
yeah.
of
It's
course.
like
Yeah.
much
I mean
better.
that's it's like the Space Ecology Workshop, but in person. So I would recommend everybody go.
Yeah.
Um, okay. Well, we're here at 12:30, so lunch is finished now. I hope everyone had a nice break. I had some vegetable soup. And I don't want to take any more of Davi's presentation time, so I'm gonna go ahead and let you tell us all about vertical farms to space analogs, the standardized terrestrial platform for space ecosystem technology research and training.
Oof, a long one.
It was a big one, yeah.
Thank you, man. Can you see my screen?
Yep.
Oh, perfect. Okay, so hello everyone. I hope you had a great lunch. Good afternoon from Brazil. It's a great pleasure to be here. I would first of all just congratulate Patrick to organizing this exciting workshop. Has been very insightful with really great presentations. Well, the topic of my presentation now, I'll be discussing about vertical farms to space analogs, which I will be focusing on the standardized terrestrial platforms that will allow us to do some research and training on space ecosystem technology. Yeah. Well, this is the summary of my presentation. I will start with some initial considerations, which is mainly the motivation that led me to, let's say, dive into the topic of standardization. This will lead me to talk about some standardization efforts in the field, especially regarding space applications. This will also allow me to discuss about some applications for the space analogs. And lastly, I will be talking about some potential results and outcomes that we are expecting with some initiatives, with some exciting initiatives. So the first the first thing that I want to point out is that both CEA and Space CEA, which is a term utilized, proposed actually by our last presenter with other colleagues, Luke, which stands for Controlling Environment Agriculture for Space. Both fields of research, we identify that it has some specific technological challenges. This requires some collaborative inputs from professionals in general involved in farming research and also commercial farming facilities. Based on these challenges, I wanted to just highlight some of the consequences of them. The first thing is related to the production of data. And this is exactly what Professor Volker mentioned in his presentation earlier, that he cannot just reproduce his experiment, especially if he wants to reproduce this in different places. So this is exactly what I'm highlighting here, because of course, we'll have different equipments, different requirements, different structures, and this is very tricky if we want like to produce similar data for different system models. The second point is that the comparison of target data from different initiatives and facilities is limited. And just to exemplify this, let's consider that I'm here in Brazil doing research with artificial lighting. Actually, the responses of a specific crop, let's say lettuce, in artificial light with artificial lighting, and there's another research in the US doing research with lettuce also, but his aim of his research field is more on the irrigation system. So both of us will be providing, will be generating lots of data on the physiological responses, but also we'll have our target data, which is, in my scenario, the lighting, in his scenario, the irrigation. So, but unfortunately, most of the time, this data cannot be compared. We cannot extrapolate because, again, we have different structures and different control hardwares and also control algorithms. And this kind of limits how the way that we can analyze the data from different angles, still if we are dealing with the same research field. Well, with that, my research specifically here in Unicamp, I came up with the hypothesis that if we implement some standardized approaches, we can provide a better understanding on the interconnection, impact, and dependencies of farming system. This is what I call the plant system environment interface. For now, not adding the human, but of course, we all know that this will be another very important step that will impact all of this this interface. So, but also, I want to bring another example, more on the vertical farm industry, because we already know that they have many similarities with what we aim for space farming. So if we implement standards, of course, we are talking about companies. They want to promote scalability and increase the productivity area. Also, there is a need to adapt their systems requirements and management practices to promote adequate conditions for different crop species. And with that, that's why I bring the figures of this vertical farm, which I had the opportunity to work for a while there. Pink Farms is located in São Paulo. From left to right, you can see just an example of the systems, the vertical structure that they utilize on the left to grow microgreens, and in the middle to grow lettuce. And what if they want to grow strawberry? Will they create a new structure for it? So this is kind of another limitation, and well, this is what led me to also get even more motivated to talk about standards and standards for indoor farming, space farming, controlled environment agriculture in general. Also, as we know, we need the efficient use of space in these confined volumes, and to optimize the structural design, to streamline operations. We are already having some solutions like robots and other automation solutions that are being benefited with some standards, but of course it's necessary to have a very very clear understanding on the operations itself. And finally, to simplify the product design, and this is very important if they are looking for financial investors, because they need to reproduce that CA configuration in different places if they want to prospect. Well, basically they validated their system in one specific location, but this doesn't mean necessarily that this is validated for another location. And if they can ensure this, we can start discussing about some increased maturity levels for the industry. Now, talking about some standardization efforts in the space exploration context, I bring some strategies mainly related to hardware, software, and data gathering. And with that, we can consider that this is good. This facilitates the establishment of metrics, especially if we want to ensure interoperability, flexibility, efficiency, and safety. The examples here, as you can see, the first one on the left is the biomass production chamber with a diagram showing like how the monitoring and control subsystem is interconnected with the other subsystems. The other example is the Eden ISS, which operated in Antarctica for almost 5 years. They had this control and data handling system, which is basically the main control interface, the main control hardware, having an interface with the sensors for different subsystems, and also they controlled utilities. And also this has another interface with an external user interface to get data and so on. In a similar, with a similar effort, in a similar way of thinking, very recently, me together with my colleagues Sarun and Stephen Lenting, we proposed a new strategy based on the bridges methodology. I will not discuss about bridges because I had the opportunity to talk about this in the previous Space Ecology Workshop. So if you're not familiar with this, I highly recommend you to check the link that I put it here that discuss more about this initiative, this methodology. But the idea with this standardization strategy that we created very recently is that we have three main subsystems, which is the atmosphere management, illumination, and nutrient delivery, and they are responsible to manipulate the microclimate where the plants will be growing. But to do this coordination among the systems, we have one unified or one control unit that will have the controller, the microcontroller, for example, and will interface with the monitoring devices, will provide the automation capabilities, and also the connection with a database or like providing a dashboard for users and so on. Led by this initiative, we started also to evaluate some ways of applying, of implementing these standardization efforts in the space analogs. And while I was doing a literature review on this, one interesting thing that I figured out is that we have some limitations, such as irregular structures, as you can see in the figures, in different space analogs, missions or stations, and also the lack of standards for data collection. For example, we have sensors positioned in different places, and how can we ensure that this is the best place to position a temperature sensor, a relative humidity, a CO2 sensor. And these divergences of positioning and other features related to equipment and so on, this also leads us to these limitations. And I consider that overcoming this limitation will be very crucial if we want to better understand how future space ecosystems will function over longer periods of times, because in the analogs, we aim exactly to understand different mission scenarios with different analog astronauts performing that specific mission to reach a specific goal for that mission. So, and this is very useful because if we are considering future space ecosystems, we'll have different scenarios, different mission scenarios. We'll have different situations. We want to start with a small system and we want to expand this. But if we do not collect proper information, if we not have proper insights from how these are linked among each other, I think it would be very difficult for us to get proper insights, proper useful information that will allow us to, for example, handle a problem, an issue that will be happening in this ecosystem. So dealing with that, motivated by this limitation, this was a result from the presentation in the previous Space Ecology Workshop. When I presented bridges, we had the opportunity to connect with other researchers, with other professionals. Here you can see only their affiliations. The institutions are not working in this project. I want to mention that. We are working on this project as individual researchers, but it's just for you to have an idea on the diversification of experts, of professionals that are putting efforts into this project in an international context, of course. Well, with that, we aim to integrate the Space CA cabinets proposed by, which is a system developed by the company Growbot Systems, and we want to implement this during the world's biggest analog mission in 2025. The main idea is to evaluate the interoperability of the systems and provide some centralized data collection protocols. The topic that we also want to investigate is the social-cultural context which professionals from the UCL, on the anthropology side, they are very interested to understand how this socio-cultural background of the analog astronauts will impact on the design parameters of the chambers, of the cabinets, also on the logistical constraints, and mainly on the human interaction with the systems. So to conclude my presentation, just providing a brief overview about these potential results. This is very interesting because Dr. Oscar Munge yesterday presented the scales of bioregenerative system, and in here I'm just adding, let's say, the standardization as a tool into this scale. So the first point, we have the demonstration based on the space farming research conducted along the years. Then we have the integration part, but not only the integration between the space farming solutions, but also we can integrate with the modern terrestrial farming systems. And I want to highlight here that most of us that are involved with space, we are aware of it. However, people who are involved with the terrestrial farming systems, most of them are not. So this is a double way effort. But for now, let's focus on the integration that we have a lot of technologies and capabilities of systems that we can implement in a process of continuous improvement of these space ecosystems technologies. And I just put these figures to provide a better an idea that we have different initiatives, but they're very similar inside of them. From left to right, we have the Eden ISS, the Biopod by Interstellar Lab, and also a concept by NASA of a space greenhouse. So if we implement all of these, if we reach this scale of doing this continuous improvement, we can start implement some solutions to achieve controlled closed ecological life support systems, and of course, consequently, providing some refinement to reach a bioregenerative life support system. So, of course, I should not forget about the technology transfer, as we all know that we can offer to these modern terrestrial farming systems. And finally, our aim with this, of course, we are still working to make this happening. So it's a kind of also an invitation. If you are interested to know more about the project, and if you are willing to collaborate with us, feel free to reach out. But our aim is that we want to turn the data into insights to provide this appropriate management and support decision making. So with that, we want to facilitate the comparative analysis of across these different experimental conditions, production setups, and mission scenarios. And with that, we are also putting efforts to develop some unified metrics to integrate these technical and non-technical requirements, take into account various technologies and maturity levels, because as we know, like if we are dealing with commercial equipments, they have different requirements, technical specifications, and so on. But with that, we want to focus more on the species, the cultivars that we are dealing, the phenological state of the plant, the stressors in the environment, and these will be the operating parameters that we will input to generate some relevant production relevant objective functions, and consequently to come up with some data-driven control architectures. So that's all that I have for now. Thank you very much for your attention, and I'm open for questions if we have time. And feel free to connect and contact if you find relevant. Thank you.
Thanks, Davi. That was really interesting. I can see the parallels between this and your previous talk in Bridges. I am glad that someone is going through the hard work of trying to get everyone on the same page, adopting standards across the industry. I hadn't considered it before, but I liked the illustration of the biopod next to the NASA greenhouse and the Eden ISS, because it is interesting how many of our solutions converge on the same form factor. And when that's the case, why aren't we standardizing them? Yeah, really good insight.
Sometimes we think a lot on the structure, but at the end, we are not interested in the structure. We want to grow the plants. And if we can have the operations that will allow us to do it, the control systems, the system, how the control systems will manipulate that environment. The plants will perceive the environment. They don't care if they are in a in a shelf or like. So that's the idea that came up with this standardization efforts that I presented.
Yeah. I don't see any other questions, so I guess I'll just keep asking. That we've agreed that the solutions often look pretty similar, but especially in cases where we're doing, I guess, innovation, like in the example, the kinds of differences you would have between ground-based hydroponic systems and a potential microgravity one. Do you think that it's possible to apply the same standards to these new situations, or what's your approach there?
This is one thing that we are still like evaluating. Like this
Mm,
is mainly the thesis. This is my thesis here at the university. So what I'm trying to understand is that okay, if I have the input parameters that I desired,
mhm,
and let's say that these input parameters are the data collected on microgravity, and if I put this, if I have this input in my control system, it will perform in a way that will control, it will manipulate the microclimate to provide the similar environment. Of course, we cannot provide like gravity, like lack of gravity or radiation, but at least the environment, like the parameters like temperature, relative humidity, VPD, the lighting levels, and the spectrum anyway. So if we can provide this and like I'm pretty sure that we have better ways of comparing this data. So let's say
mhm,
that we have a greenhouse operating on Mars and we have a lot of inputs from the data of it, and we want to replicate what is happening here. Imagine like the regolith, like what happened with the regolith. They collected all the parameters of the regolith and they implemented a simulant. So imagine that we can do this with the systems. Of course, like there are many systems limitations. For example, if you want to grow microgreens, I can utilize a LED lighting that has less light intensity, that provides less PPFD, but which is different if you want to grow wheat, for example. So, but imagine that we want in the same system to grow microgreens and wheat. So imagine that if we have a lighting system that has a higher operational range, a bigger operational range, we can exactly like, okay, now I want my control system to perform in the desired way for wheat, or I can control I can put my control system to put the light to perform in the way that I want for microgreens. So I don't need to
mhm.
change the technology. I just need to change the input parameters. So this is kind of the efforts that I'm putting here, like to try to replicate these environments. And of course, like that's why we have this team of, it's not only me, but like I'm more focused on the hardware, but we have like Luke, Tarun, Stephen, like and many others. We are evaluating different features that will, let's say, put everything together and take the most of this multidisciplinarity of space farming, of space exploration.
Yeah, that's right. You do have quite the dream team over there. It's a lot of familiar faces. We got to move to the next presentation, but thanks a bunch, Davi. I'm sure I'll see you next year. The next person on the list today is Gavin Schneider, who is presenting perhaps a complementary presentation to the earlier Interstellar Labs presentation. I'm sure he'll go into more detail, but there were actually two deep space food challenges being run concurrently. And while Interstellar won the NASA one, these are the winners of the Canadian Deep Space Food Challenge. So, uh, Gavin, please go ahead.
Excellent. Thank you. Thank you for the last presentation. That was excellent. 1 second. Okay, is everybody able to hear me and see my screen here?
Yep.
Okay, excellent. So yeah, thank you for putting on this workshop here over the last 2 days. I've been able to pop in and out here over the last couple of conversations. So yeah, my name is Gavin Schneider. I'm one of the co-founders here of our new company called Next Planet Technology, which is really an offshoot of the Deep Space Food Challenge, which was the competition that we won earlier this year. So many of you here are obviously quite aware of this 3-year-long challenge, which there was a NASA competition, and then on the parallel side, there was the Canadian Space Agency, which was running a similar program over the last 3 years. So we originally applied for this in I suppose it would have been 2021. It's been a long journey to get to this point where we ended up coming out on top. And so this was I think there was over about 70 applicants into this competition at the very beginning. And just for some context here, the program was entered in through a company called Ecoation, who I was the vice president of agronomy for at the time. And we had a team of engineers, scientists, agronomists, really all working on this challenge over a number of years. So myself and my co-founder, Steve Humston, did the original design for this, which we called CanGrow, which was homage to the Canada Arm. So the challenge asked us to come up with a food production system that could feed 4 astronauts on a 3-year mission to the moon or Mars. And it had to fit very specific spatial requirements and food output requirements. So what we came up with over the course of the years was our CanGrow system, which is a polyculture food production system, which is able to produce a number of different crops here. So in April, we were very lucky to have the Commander Chris Hadfield send us a personal video congratulating us for the win, and we ended up getting a ton of press for this. So just kind of for context here is Ecoation was really the parent company that started this, and now we have our spin out 2 companies. So Maya Farms, which is I'm the CEO, and which is now my day-to-day job, which is where we are now commercializing our mushroom mycelium production technology. And then Next Planet Technology, which is we are specifically focused on food production for space applications, directly using the technology that we developed over the course of the last 3 years. So over these 3 years, there's been incredible impact. So what we've been able to do as a team with our really deep experience in food production and food production technology is really establish ourselves as a leading company and commercial private company that has laid a foundation for a Canadian agriculture company to lead in this new space. I don't want to get into too much of the technicalities in my presentation today of what we've done, but I just find it incredible that we have all of these different ideas and the way that these technologies are not only able to solve these problems for food production in space applications, but also in terrestrial applications, which is really where my background comes in. I've been working as an agronomist here for the last 10 years. Sorry, 1 second. My daughter just came. Sorry. Yeah, so is my screen changing here? Is everybody able to see that?
We're on impact right now.
You're on. Okay, perfect. Yeah, just want to make sure that's clear. So, yeah, so in April, the announcement came, and really what we've been able to do is turn this into a number of different private companies, and we're now in collaboration here with the Canadian Space Agency, and I'll dive into the work that we're doing there right now. So just in terms of the team as to who is leading the Next Planet Technology. So myself, I really lead here on the agronomy side. Dr. Mir Smalley, who is the founder and CEO of Ecoation, and then Steve Humston, who is an industrial designer, and then Chris Okenritz, who is our lead mechanical engineer. And so the 4 of us are really kind of combining our expertises to form this company. So our system here is about the size of two small fridges. And over the course of the years, there's been a number of different prototypes built. But really, this is a complete food production system, which is able to run on very low power requirements. It's able to connect up to a single 3/4 inch water supply and semi-autonomously grow over 750 kilograms of food annually. And that's, you know, an incredible number, but this is a combination of the technology, of the plant selections that we put in, and then also on the mycelium biomass fermentation, which I'll get into a little bit more as to what that technology actually is. But what we were trying to achieve is maximum nutrient diversity with a combination of a diversity of food that is able to complement the nutritional needs of a crew of 4 astronauts. We obviously there, you know, over the last 2 days, we've gone into so many of the technical challenge and, you know, the deep science, the deep mathematics, the deep chemistry that goes into this. You know, what we really focused on was applying readily available technology that we were able to, you know, number one, know that we were able to produce which crops, and that we were able to actually put this into a complete integrated and working system that minimized the amount of operating time and the amount of maintenance time that goes into this. So there's all sorts of various different technologies that go in here, but everything from UV water filtration systems to, you know, a specific AI climate control system to different cameras. So there's an incredible amount of technology that's gone into this, and all through this we've tried to minimize the amount of substrate that we're using, and so the system is set up to produce both hydroponically, aeroponically. We're able to use rock wool, we're able to use peat moss. So it's really all about flexibility for the operator, and then also with the view that this technology should have terrestrial applications, and you know, particularly in the Canadian context. When we look at food insecurity in northern Canada, we need decentralized technologies that are easy to operate and culturally appropriate. And this is really a big part of the design decisions that we were able to do. So, you know, in terms of the final output of the final can grow system that ultimately we won the challenge with, we focused on 3 different crops, that being strawberries, which, you know, I can go into a bit about the technical challenges of producing strawberries in this system. We were producing dwarf tomatoes, lettuce, microgreens, and then we also had, over the course of the 3-year journey, we also worked with dwarf cauliflower. I worked with dwarf radishes, beets, and then we also incorporated a spirulina unit in this as well. And then, but the big part here is the mycelium bioreactor, which is what you see there on the left, which is, you know, now my spin-off company, and where we now employ 10 people, and scaling this technology to, you know, ultimately thousands to millions of liters of production capacity. So, you know, there's been really some incredible work that's taken place over this, and the different kind of engineering efforts that have gone into this is, you know, for everybody from software engineering to mechanical engineers and electrical engineers. Myself on the agronomy side, we've had a neuroscientist working on this. You know, it's just really a complete team effort to be able to do this, and this was all. You know, I want to stress this was all on volunteer time. We all had, you know, regular day-to-day jobs through this, and we were working on this solution for 3 years, after hours, on weekends, to ultimately build what the can grow here is. So I'm going to talk a bit more about the AI environmental control. So we wanted to minimize the amount of operating time that somebody would have to go into this. So I have a background in building and operating large total controlled environment growth system. So, worked with, many different companies from the Netherlands. These are large, greenhouses in addition as well. And so there's a number of existing technologies when it comes to environmental control that we took inspiration from. But what the challenge is, it's much easier to maintain a climate in a big space than it is to maintain a perfect climate in a very small space. So what we implemented into this was various different sensors. So CO2, relative humidity, temperature. There's AI-driven cameras, which I'll go into a little bit about that, and the equation technology that was incorporated into this. And then all of the closed loop fertigation system that goes into this, manual disinfection processes. And then ultimately, we focused on technology that would minimize the amount of operating time. And over this course of the last 3 years, I was the individual operating this machine, growing the plants, really collecting all of the data. And what we were able to do is get this unit down to less than 4 hours per week of manual operation time. And that's everything from the nursery side of seeding plants on a weekly basis, trimming the plants, cleaning it, making sure that kind of all the system checks are in place. But what was really challenging for this specific competition was, we had a year from receiving the seed funding to build the technology after we won the first top 10. We had to build it, we had to operate it, we had to grow the plants, harvest the plants, and get everything tested for food safety. So you can imagine during that time there was just so much happening. And you've got engineers, putting the water system together while I'm, over top, actually growing the strawberries. So, it was just really a lot of fun during this time. So, one of the systems that I'm most proud of here is the dwarf tomato production system, where we were able to achieve yields of about 110 kilograms per meter squared per year. And in the context of tomato production, that is phenomenal yields. And I attribute that to choosing specific cultivars in combination with the environmental control systems, and of course using dynamic LED lighting through the production cycle, optimizing the timing of the flowering and the pollination that go into this. But it's it's very easy to grow lettuce in a controlled environment production system, but it's much more harder to produce fruiting crops. And I also mentioned that we were doing lettuce through this here as well, or sorry, not lettuce, strawberries. And one of the challenges with strawberries is that you're not going to grow this by seed. So one of the technologies that we did implement in one of our earlier prototypes was a tissue culture nursery for being able to do micropropagation for high density plants grown on agar. And so that's one of the technologies that we really see as crucial for establishing higher order plants. For example, if you ever want to get into exploring dwarf banana species, you're going to have to implement some level of micropropagation for plants that do not grow by seed. So with the strawberry systems, we faced those challenges. In 2022, I was actually able to move the vegetative propagation to a seed strawberry, and I worked with a specific Japanese seed supplier, and I was able to demonstrate some of the first strawberry fruit produced in a total controlled environment system like this. And then you'll see there on the right is the equation forecasting technology, which is used in commercial tomato, pepper, and strawberry greenhouses. But really, this is an AI-driven camera system, which is used to identify, track, and count different fruit within a canopy. And this is typically used in the context of a 100-acre greenhouse. But we were able to also implement this into our technology here for tracking yield growth over time automatically. So there's just we were able to kind of pull so much together here, and then a big part was on the lighting systems that we chose. There's over the course of the last 10 years, there's been a huge developments and improvements in LED technologies, and I've been there for every step of the way and evaluating different lighting systems. We were able to really find a lighting solution which was fully customizable, tunable LEDs with intensity and something that was ultra thin and did not heat up the overall environment more than even some of the best performing systems on the market. We looked at implementing a standard Fluence or Philips lighting systems, and what we were just limited by the actual structures themselves, and we ended up just building our own lighting system ourselves with the software control for this too. So I'm going to talk about the liquid fermentation mycelium bioreactor. So mycelium is the root structure of mushrooms. So we all know that you can't grow a cow in space. You're not going to bring chickens to space, and I also have my doubts that even some of these higher protein, cricket solutions are not suitable for these long-term missions. So at the very beginning, we looked at a aerial mycelium solid state fermentation system. That was back in 2020, and we were originally proposed what we called a space bacon, which is growing a aerial mycelium mass, and that is able to grow out of the substrate. You're able to cut and harvest this. That faced technical limitations when you had this in a very small environment, and it was also due to the incredible high amounts of CO2 that were required. So over the course of this period of time, we really actually dove into liquid state fermentation technology, and this is the the spin out of my own company now here, Maya Farms, which
Hey, I really apologize for interrupting, but
yes.
we're at the end of this time slot.
Oh, okay, sorry, my bad.
Yeah, sorry, it
Yes.
was only 20 minutes.
Oh, okay.
And this is
Apologize.
disappointing because I really wanted to hear about this
Yes.
mycelium bioreactor.
Okay, no
What's
worries.
the best place for us to follow up on more information?
So right here, you can email us here at founders@nextplanet.tech, or you can email me at gavin@mayafarms.ca. And I just want to start, or I'll just finish by saying that our system is at the Canadian Space Agency today. So if anybody here is part of that contingent, you can go and see that there are actual future astronauts using and evaluating our technology today. And and I had the privilege of spending a week there in May, and we're there now on a monthly basis, working with them and finding improvements. So these commercial applications happen, and these actual technical applications happen. So yes, sorry.
Yeah. No, I'm really sorry to cut you off. Please, people, put some comment or put questions in the chat, because I want to know more about the mycelium bioreactor. But we have to move on to our next presenter, who is Ravi Hosamani. And he's going to be telling us also about lunar regolith and plant growth. Ravi, are you here? Or I guess I also see your PhD student, Basava. Are you going to be presenting today?
Yeah, yes, I'm here.
Okay, great. In that case, I would like to introduce Basava Swami. Yeah, please go ahead and tell us about lunar soil nurturing plant growth.
Yeah, thank you for the opportunity. Yeah, let me share my screen. Yeah, I hope my screen is visible. Yeah, thank you. Thank you for the opportunity. My name is Baswalinga Keswami. So actually, I'm here presenting on behalf of Dr. Ravi, my professor, Dr. Ravi Kumar Hosmani. He's absent today due to some official tour. So I'll be talking about how can the lunar soil nurture plant growth, whether it supports. So we have done a preliminary experiment using a lunar soil simulant. So that study I'm going to present here. Growing plants on the lunar regolith. So the lunar exploration and growing plants on the lunar regolith has captivated a significant attention in recent times through programs such as Artemis. So to establish the long-term sustenance on the moon, astronauts has to grow their food on site. So at the present, we have hydroponics and aeroponics are the viable options. So, however, the utilizing the in situ resources such as like regolith on moon for crop growth offers a more sustainable approach. So, lunar regolith, as we know, the lunar soil or regolith primarily comprises the fine particle or rock and dust containing the minerals such as silicates and pyroxenes and olivines. So with this, there are like a lot of challenges to grow plants on the lunar. Of course, the environmental factors, many like space radiation and less partial gravity. Apart from that, there was the lunar regolith itself poses many challenges for the plant growth. Especially the presence of the dust particle in the lunar regolith induces the mechanical challenges to plant for penetration of root and the absorption of the nutrients. And another thing is there is a absence of weathering processes and microbial activity that hindrances the nutritional cycle in the plants, and the lack of organic matter and essential nutrients in the lunar soil. So the thing is to carry out such studies on the lunar regolith, we don't have that much access at present. Given the limited access to the real lunar regolith, the use of moon soil simulant becomes indispensable for the researchers. So over the decades, lunar exploration mission have provided comprehensive information about the mineral composition and the chemical properties of the lunar regolith. So that enabled the researchers to simulate the physical and chemical composition of the mineral. So with that, several space agencies, space institutes, and they have developed the lunar soil simulant, especially if we talk about NASA that has the JSC1, and recently, some 2-3 years back, ISRO has developed a lunar soil simulant called LSS ISAC1. So that they have developed using the terrestrial and anorthosolic rocks to mimic the geotechnical properties of the highland soil of the lunar surface. So here you can see the lunar soil simulant that has been developed by the ISRO. It's made from the rock and looks like a cement. So with this, actually, we have conducted a preliminary experiment with the limited resources what we have in our country. Initially, we have conducted the experiment using the lunar soil and with the comparison with the earth soil. So we have selected here the 4 crops with the as the indication of 4 different things, like one is field crop, and then is vegetable crop, another is oilseed crop, and another is cash commercial crop. So wheat as a field crop, and tomato, vegetable, and groundnut, oilseed, so cotton, to represent all different groups of crop plants. So we have taken 4 different crops, and initially we have grown this plants with the minimum quantity of lunar soil available with us using cellular pots. This is the results we got when compared to the earth soil and lunar soil. This is the wheat and tomato, groundnut and cotton. So we found a germination, good germination in a wheat when compared to earth soil. Even in a lunar soil, we got the good germination, but in tomato, a low germination. In other crops, the two crops, we got a germination then. But the growth of the plant got hindrance completely. You can see in the picture, especially in the wheat, a little root has been developed, but not proper root development due to the penetration. The lunar simulant was very like, it was like a cement effect. And another thing is tomato has shown a drastic reduction. It completely, the plant got died. You can see the pictures here. And that groundnut even after some days, some 3-4 days, even it started showing decay or something, death in the crop. There is no root growth in the plant. And even cotton was horrible. It didn't show any that much growth. After some days, completely it got died. So with this, we just thought a plan of like using any natural material, so our resource that we can that we can ameliorate with the lunar soil, just to improve the quality of the soil and the aeration, all those. So then we thought about the cocoa peat. Cocoa peat is a versatile, it's a natural fiber extracted from the coconut husk, and it's rich in the fiber, and it has a different properties of holding a good water, and that promotes a strong root growth and plant, and especially rich in the nutrients, and can be reusable. So before proceeding with the before supplementing cocoa peat with the to the lunar soil, so we have just checked the chemical properties of all three types of soil which we have used in this study. There's a lunar soil simulant, and the earth soil, and a cocoa peat. So we have tested the pH, electrical conductivity, and then the minimum different macro and micronutrients. So pH, as you can see here, the lunar soil is possessing a high pH, and compared to the earth soil and the cocoa peat, whereas cocoa peat, it's a low pH, and even micronutrients, it's there are a lot very less quantity of micronutrients and macronutrients are present in the lunar soil. So with this, we just thought of just ameliorating the cocoa peat with the lunar soil similar. So with that, we have supplemented this cocoa peat with a different concentration to the with the lunar soil. So these are the different groups we have done. First, the earth soil and the lunar soil, 100% lunar soil. Then we have ameliorated the soil with a different cocoa peat percentage. We have started with the 3.125%, and with the doubling percentage, 6.25, 12.5, then 25, 50, then 100% cocoa peat. So with this, we have started the experiment growing the crops. First, we have grown the wheat. So this is the results we got when we grown the wheat in a different varied concentration of cocoa peat and lunar soil. So this is the first one is earth, and the second one is the complete lunar soil, and this is the 3.125% cocoa peat amelioration, and 6.25, 12.5, 25, and 50. It's 100%. As you can see, the growth in the complete cocoa peat, the growth was very good, and compared to all other groups, the growth of the crop is very good. So here we have standardized that a percent which is showing the good result when compared to the earth soil. we found the 6.25% of cocoa peat amelioration with the lunar soil simulant has shown the significant changes when compared to the earth soil and or similar to the earth soil growth. Whichever the lower we selected the lower concentration which have been ameliorated with the lunar soil. So in wheat we have selected the 6.25% of the cocoa peat amelioration with LSS. Here we can see the germination what we found in the different groups of the soil, and again shoot length, root length, and seedling fresh weight and the seedling dry weight. So this all we have statistically analyzed with the one-way ANOVA and followed by the post-hoc Tukey test. And this again in the tomato. Tomato again we got a good good results like in again 6.25% of the cocoa peat. Then the groundnut. Groundnut has shown a little good growth in the 3.125% of the cocoa peat mixture. So these all studies we have conducted at the seedling stage. So groundnut has a accordingly we have a standard of the groundnut has a seedling stage of 10 days. So we have seen all the crops up to the seedling due to the limited access of the lunar soil what we have got from the ISRO. So then the cotton. Cotton again same phenotype we have tested, and the cotton has shown little high. It requires little high cocoa peat percentage we found here. We got 12.5% of cocoa peat is showing the a little well growth when compared to the other soil groups. So then we have tested the stress enzymes just to, as we know, the lunar regolith, it's like completely toxic to the plant. So when the plant exposed to the toxic environment, of course, it will be a stress for the plant. So here are the different groups and different enzymes, stress enzymes. We have analyzed catalase, peroxidase, polyphenol oxidase, and the total carbohydrates we have done. So you can see in a different crop, in a different soil group, we have selected here the whichever best supplementation proportion we have selected in each crop. As you can see here, in a wheat, we have selected the 6.25 cocoa peat percent, and again in a tomato 6.25, whereas in a groundnut 3.125, and cotton 25%. So you can see the enzyme expression of the enzyme, especially when in the lunar soil, all enzymes are showing little higher expression, showing that the soil is acting creating a pressure, a stress on the plants. So with this study is very preliminary and very well with the limited resources we have conducted. So the study represents a preliminary step towards the establishing a sustainable agriculture ecosystem on the moon through in situ resource utilization strategies. And the findings suggest the cocoa peat hold a promise and offers a unique opportunity to enhance the physiochemical properties of the lunar regolith. However, due to the limited access to the moon regolith simulant, our investigation was restricted to the seedling stage only. So it is essential to extend the research to encompass the entire life cycle of the tested crop from seed to seed and evaluate the effectiveness of cocoa peat in mitigating adverse effects on the moon regolith simulant. Thank you. Yeah, I'm happy to take questions if there are any questions.
Thanks for that presentation, and thanks also for filling in for your professor. I really liked this presentation because you showed multiple crops growing in regolith, which I feel like is often not the case. And also it's pretty interesting to see how the amount of cocoa peat that each plant wanted was pretty significantly different, you just assume that more organic matter is better when the mineral substrate is regolith, but maybe that's not always the case. Adam, who is going next, posted a question in the chat. I think he read the article that was published in Acta Astronautica. Sure Adam is also using cocoa core, maybe if not cocoa peat. He said, for clarification, are the cocoa peat to regolith simulant ratios you discuss percentages by weight or by volume?
Yeah, it's by a weight. So we have done the weights by weight.
Okay. Yeah, that's good to know. I think that we will see something pretty similar in this next talk from Adam. But Kevin asks, what's the benefit of growing plants in regolith compared to hydroponics? Like, why bother?
Especially the hydroponics, maybe the nutritional requirement, and the regolith, maybe when we go on board, more than depending on the all nutrition thing, we can utilize the available source, whichever is there. And yeah, nutritionally plants may change as compared to the hydroponics and the regolith. I think so.
Okay. Oscar also asked a question about water potential, but I kind of want to move on to the next presentation just so we don't get behind again. If you wouldn't mind answering that one in the chat, I would appreciate that. Great. So thanks a lot for your presentation. Actually, I have a couple questions in the webinar chat, if you don't mind. I think we're going to move on to Adam Gelman, who's a friend of mine and one of my peers at the University of Arizona. He's going to tell us about a different tact. This is the misadventures in amending lunar regolith simulant for crop production in hydroponic systems. So please, Adam, tell us about how that went.
It will be my pleasure. Yeah, this has been quite the adventure working with this lunar regolith simulant. Going into it, I was not expecting all of the physical challenges associated with this substrate. So I'm going to go ahead and share my screen. Can everybody see my screen and hear me?
Yep.
And okay, great. And it's showing just the slideshow and not the, I think it's showing the correct window, yes?
Yeah, that's right.
Okay, great. Alrighty, so I'm gonna talk to you guys about my misadventures in lunar farming, or the challenges of working with lunar regolith simulant. So this substrate is a very, very interesting one. As we all know, here I have the geochemical properties of the simulant shown. This is in particular the LRS, LHS1 simulant from Exolith. So Lunar Highlands simulant in particular. And as you can see, it's full of a lot of glass-rich basalt, anorthosite, ilmenite, and all these oxides. Not great forms for plants to absorb nutrients from. These are all crystalline forms, and mineral forms, not salts. So very unhelpful. So how do we resolve this issue? Well, I'll get to that later. But first of all, here are some of the physical properties that I encountered while attempting to just grow plants in this straight lunar regolith simulant. First of all, it's dry, it's powdery, feels almost like flour to the touch. It's very, very fine, as is common knowledge, but I'll point it out anyway. When you drop or when you mess around with this lunar regolith simulant, clouds of finer particles puff up into the air and are very hazardous to breathe in naturally, as breathing in rock dust is seriously toxic. Now, what really interested me is what happens to the simulant when it becomes wet. When you utterly drench and soak the simulant in water, it becomes almost a fluid in and of itself. This water regolith mixture, And it behaves in a relatively shear thinning manner. For those of you who are not chemical engineers or are otherwise unfamiliar with this terminology, it's hard to just press down on or just move around, but when you vibrate it, it becomes a lot more flexible. So if I were to rest my hand on it, I couldn't just push my way through, but vibrating it makes my hand slip through relatively easily. And on top of that, it also behaves in a hydrophobic manner. It separates from water like oil. The finer particles rest on the bottom of whatever container this regolith water mixture is sitting in, and water gets pushed up to the top, forming a layer of water or thin water regolith mixture on the surface, and a layer of dense, relatively dry regolith on the bottom. So how do we amend this? How do we turn this weird, not very soil-like, not even very sand-like substrate into something that plants can use, something that we can use? And so there are a few different options. There's green compost, just straight up mixing in the plant matter from previous harvests or from other sources into the lunar regolith simulant. Just putting straight algae, dried algae into the simulant. That's a potential option, or it was a potential option to explore. You can mix in plant fibers, which is what I did, and which is what we saw in the previous presentation, those coconut fibers. And there's, of course, human compost, which we've also heard about earlier today and yesterday. And we also can include living organisms, beneficial fungi, bacteria, even beneficial insects. I didn't mention it on the slide, but nematodes. There are plenty of different organisms that you can and probably should mix into this substrate in order to render some of those nutrients that we saw, or some of those elements that we saw in the chemical breakdown, more accessible to these plants. So we went with plant fibers. We went with cocoa coir, which is very similar to cocoa peat. I believe if there's any distinction between cocoa coir and cocoa peat, it's that cocoa coir is more sort of just the fibers, whereas cocoa peat is more powdery in form. And we also inoculated our substrate with beneficial fungi and beneficial bacteria. So now I'll get into the design of our system a little bit. By the way, all of this research is currently has been conducted at the University of Arizona in Tucson, at the Controlled Environment Agriculture Center. So this is the system design that we went with. This is a very standard Beto bucket or Dutch bucket system. You can see each of these buckets is filled with substrate, and the nutrient solution is recycled in a circular manner here. We did not drain to waste. We did recycle all of our nutrients. We had a few challenges with our system design, but you can see this is the setup. We had 5 groups, these 5 buckets down here. These were lunar regolith simulant that had not been inoculated with microbes. These 5 buckets were lunar regolith simulant that was inoculated with microbes. And then over here, the same sort of setup, but with perlite. This is inoculated perlite, and these 5 were uninoculated perlite. And we chose perlite as a control because it is a similarly volcanic inert substrate. And the plants that we are growing here are red robin dwarf tomatoes. And you can see here, this is the divider between each of the sections, between the inoculated and uninoculated regolith. And there was no mixture between the, despite the fact that these pipes appear connected, this is closed, so there was no mixture between the simulants, or excuse me, between the nutrient solutions, or the simulants, I suppose. So within each bucket, we utilized this design to sort of simulate, well, A, to prevent the erosion of the lunar regolith simulant into our system, and B, to sort of account for certain filtration of the the nutrient solution through this fabric mesh here and this LICA, lightweight expanded clay aggregate, these expanded clay balls underneath the fabric mesh. So water would enter from the top. Ideally, the water would have flowed through the lunar regolith simulant, gone through the fabric mesh, filled up this section at the bottom here, and then flowed down through this pipe and back to through this return stream back to the nutrient reservoir. In our initial design, we had a simple square fabric mesh sealed to the sides using duct tape. It's a very MacGyvered setup, but we figured that this would work. However, this design resulted in some very interesting phenomena. I apologize for the low quality photo, but you can see some extreme flooding over here. There was a lot of overflow. And that coupled with a too frequent irrigation interval resulted in a lot of overflow and very poor penetration of nutrient solution into the lunar regolith simulant. So drainage, in other words, was our main issue. And we resolved this rather than using an amendment to the lunar regolith simulant. Well, actually, we did first try an amendment. We tried the cocoa core, and that did nothing to help our problem here. So we tried a different approach. We engineered a solution, changed our design a little bit, and we removed the duct tape from the sides. We added fabric mesh to the sides here, creating a sort of sack, which actually you can see in this photo here. This sack enabled water to percolate through the mesh around the lunar regolith simulant rather than forcing it to go straight through to the bottom. And so this helped us, and this coupled with adjusting the irrigation interval helped us ensure that the lunar regolith simulant was being soaked and the plants were receiving water, and that the nutrient solution was not overflowing from the edge of the container. In addition, we poked some holes through the lunar regolith simulant, in some cases through the fabric mesh, inadvertently, but primarily we just poked holes through the lunar regolith simulant, stopping at the fabric mesh. And this was also intended to help water percolate through a little bit more, but since we did not reinforce the holes with anything, we didn't put tubes or anything, those holes quickly sealed up, much like sand at the beach fills up whatever holes you're digging, and resealed the system. Now, for future exploration of LRS drainage, I've been considering some ideas for how future studies might be able to approach this issue of drainage. And one solution that has been floated around that I came up with in collaboration with some of my peers here at U of A is a mechanical solution, potentially vibrating these buckets at certain intervals in order to allow for that sort of fluidization to occur. We could also attempt chemical solutions, surfactants, to prevent the hydrophobic nature, or to combat the hydrophobic nature of the lunar regolith simulant. And lastly, biological solutions. How can we create compost that we can then mix into this substrate? How can we